who has an idea of what we'll be learning about? Don't look at the slide. Some people have an idea, right? It's about SNARKs. That's, hopefully everyone knows that. Yeah, everyone knows. So who knows, who heard maybe the word SNARK before? I would hope everyone, if you signed up for this event. Maybe you only read it. Okay, well that's how it's pronounced, SNARK. So who knows, who saw a thing with a picture of a cave or something like that? Who has that at least that kind of level of understanding of what a SNARK is? Yeah. Who knows what Groth 16 is? Okay. Who knows roughly what SNARKs afford you in terms of privacy and scalability and all that? At least one of those two things. Okay, all right. So we have we got some experts in the house. But if you don't know, that's fine because that's why you're here today. And in particular, here's what we're going to cover today. What are SNARKs useful for? How to use them in the context of a full application. Okay, because very often you'll see who did a SNARK tutorial and they were like, geez, SHA preimage, who cares about that? You know what I'm talking about? Yeah. Who knows what I'm talking about? Some people. But we'll see them in the context of a full application. So you'll really understand, okay, for me as a programmer, what new power do I have before that I didn't have after? Okay, that's really what I'm trying to get across here. Are we going to go into all the technical details? Maybe, if there's time and if people want to. But that's not what I prepared for. And in particular, in the context of full application, you'll also learn how to program using snarky, which is a DSL for working with SNARKs. Okay? So that's to give you a little idea. Now, I said we're going to learn about it in the context of full application. I have recently started saying snap. I know it's a really stupid word. I know it's stupid, and I know it's vague, but I really think it points to something useful. I started saying snap to mean an application that uses SNARKs. I know that's really dumb. I know it's what? You don't call it a WAP, but you do call it a web app. So you could call it a SNARK app. Maybe that's a better name, but snap, OK? So it just means an application that uses SNARKs. But really, no one really cares about SNARKs, right? A user, they're like, yeah, I don't care about HTTP, right? I go on a website, I don't care about HTTP. I care that I have an image now on my screen and my computer, wasn't touching any wires or whatever. Or I don't care about Wi-Fi. So what do you care about with a snap? Well, a snap gives its user strong and verifiable, at least in principle, guarantees about the behavior of that application in such a way as to preserve as much of the user's privacy as possible, or perhaps as convenient for the application developer. But really as possible. I mean, that's the ideal that you would hope to strive for. So I want to give this motivating example just so you can understand more what is the power that I will have after today that I do not have right now. And it's this. Imagine the following application, OK? So who here has a job? If you're not raising your hand, you're a very lucky person. Most people have jobs. Most people work at a workplace. And in a workplace, it can sometimes happen that one wants to express an opinion, but one perhaps has some fear of retaliation from an employer, from another coworker who's very judgmental. I don't know. But it happens. And so one application that you might want to make for this sort of setting is like a simple voting app, right? Where people could post topics, and people could say, yes, I agree with this, or no, I do not agree with this, for example. OK? But in such a way that you don't reveal any information about you when you make a vote. OK? Do people see where I'm going with this? Yeah, like a secret ballot election or vote. So for example, maybe I made this mock-up. Maybe some votes, these aren't that controversial, but we should use a carbon-neutral cloud. Maybe you're concerned about climate. You could vote on that. We should be prioritizing bug fixes more. And this one is restricted to the engineering team. Let's say only people on the engineering team should be able to vote on this. Maybe you say another election. I'm unsure of our product direction. OK, people are a little split on that. So is the idea clear? And who's like, yeah, I know how to build that? Who feels that? Oh, do you know how to use SNARKs?
Oh, with SNARKs? No.
Without SNARKs?
Without SNARKs, maybe.
Wow, OK. We have an expert over here. But anyway, most people probably don't, right? Because it's like, OK, yeah, like it kind of seems like there's going to have to be this central server that like everyone's going to have to register with and like submit their votes to, right? It kind of seems that way, right? And the server is going to like check everyone's, oh, is this user authenticated to vote? Are they inside the organization, right? It seems like it's not possible. After today, actually, you will understand, no, this is possible, and actually, not only is it possible, it's actually, I don't want to say, it's not that hard, OK? Yeah, so I don't know if we'll get all the way there, but we'll get close to implementing like a full version of this application in a simplified setting where like the set of voters is fixed. You can handle the case where it's like open enrollment, but it's a little more complicated, so we'll not talk about it today. And we have a working demo. Well, working, I don't know. We have a demo of this application. It's full, Node. There's a Node.js, JavaScript server. Everyone can vote. It will be very cool, maybe. So OK, we don't have to go into all the details now. Who feels motivated? Who's like, yeah, that would be cool? Pretty good. OK. So we don't have to talk about the details. Let me just give you, this is like the one-slide summary of SNARKs. Credit to Nathan, who made this dot file. Is that what it's called?
It's actually a text file.
Who made this text file, which then was run through a program to produce an image. This is the one-slide version of the functionality that you achieve using SNARKs. OK? What is it? SNARKs, how do we understand things as programmers? Yes, that's true. But maybe more specifically as programmers, we understand things in terms of, OK, like what are the functions and what's the data, right? Maybe if you're an object-oriented programmer, you only think of what are the objects. And it's both of those things. But if you're a programmer, that's what you think about. What are the functions? What's the data? With SNARKs, what are the functions? You have prove, and you have verify. OK, so prove, it means the following thing. It's a function. It takes some data. It takes some public data, and it takes some private data, and it produces something called a proof. OK, and what this proof is going to say is, I actually know some private data such that if you take that private data and some public data that we all know and feed it into some algorithm, into some function, that function will spit out a particular value. We'll see more examples. But if it's not obvious, like, don't worry. We'll do example. We'll do the hash pre-image. I know it's boring, but we'll do it. And once you produce a proof, OK, like what's a proof for? Well, it's for verifying. So then later on, someone can come look at this proof. They can look at the public input, but they don't look at the private input. And they can check whatever that means, this proof. OK? And the thing about a SNARK, this proof is tiny. So it's like, you'll see it. It'll get printed out on your console. But it's like a couple hundred bytes, something like that. And it takes like very little time to check, like some 10 milliseconds or something. OK? So that's what makes it a SNARK. SNARK means tiny and easy to check. Who's with me? SNARK, tiny and easy to check. OK. Aren't we having so much fun? Who's having fun? OK, great. So yeah, we'll skip this. What did I want to go to now? Oh, yeah, please.
I have a quick question about this slide. So is this specifically a zk-SNARK? Like if you remove the private information, is it like a normal SNARK, or are all SNARKs conforming to this?
So that's a very good question. Who heard about zk? Who knows what is zk? zk means zero knowledge. it means like information hiding. Like I don't give you any of my knowledge, you have zero knowledge. You can have SNARKs which are zero knowledge, meaning they hide all information about the private input. And you can have SNARKs which are not zero knowledge, meaning they may leak some information about the private input. And you can even quantify the amount of knowledge, right? So there's zero knowledge, but you could also have like 1-bit knowledge, 2-bit knowledge. Anyway. All right. So let's do everyone's favorite boring example. Sorry, everyone's favorite very exciting example. Again, OK. So here we have Alice and Bob. This is Alice Waters, local celebrity and chef at Chez Panisse, if anyone is familiar. Alice would like, Alice sends Bob this big blob of data, all right? The hash of something, all right? Alice sends Bob some hash. OK, why not? But let's say, Alice would like to convince Bob that this blob of data she sent him, it's really a hash. OK, you see what I mean? Like, I could just send you some random bytes, and I'm like, yeah, that was a hash. And would you believe me? If I send you some bytes, is this a hash? Maybe this is a hash. Who believes me? This is a hash. This random string on the screen right now. Does anyone believe me? Huh? What? I seem like an honest guy? You don't know me. No. Huh? OK. No. OK. All right. Sad truth. I just send you some bytes, right? I just send you some bytes. You don't know anything about these bytes. I just send you some bytes, right? What do you know? What do you know what it is? You don't. To you, it looks like this, just a blurry mess of nothing, right? To Alice, Alice knows. Alice knows that really it looks like this, right? It's the hash of something, right? But Bob, all Bob can see is this, OK? So what SNARKs, they really let you do is they let you sort of selectively reveal some computational information about data. SNARKs let you reveal computational information selectively about data. OK? So Alice can send Bob a little SNARK along with this blob of data, which says, this is the hash of something. OK? And now it would look like this to Bob. He would see it through this snarkified lens, and he would say, yes, this blob, it's a hash of something. What? I don't know, because zk-SNARK, right? But I know it's a hash of something. OK? Make sense? And by the way, here's the amazing SNARK thing. Maybe this hash function is really complicated, right? Maybe it's like, I know hash functions are usually not very hard to compute, but maybe this is like this one. Maybe this hash function takes an hour to compute. I don't know. Could, right? The amazing thing about SNARKs, Bob can perceive this fact that it's the hash of some data instantly, without needing to think for an hour. So that's really an amazing thing, right? He just looks at it through this SNARK lens. He's like, yep, that's hash data. I know the hash function would take me an hour, but you already did it, so I don't need to do it again. OK? So that's the succinctness part. We have succinctness. We have zero knowledge. It's a zk-SNARK. OK. So one thing, we just need to know one thing. We need to know more than one thing. But for now, we'll learn one little thing, which is, for better or worse, at the moment, you need to know what a field is in terms of SNARK program when you're programming SNARKs. OK? Who here knows what a field is? Don't worry, because I'm going to tell you. If you know what it is, but if you don't worry. So a field, it's like a type, OK? Who knows what a type is? Everyone, right? Yeah. A type is like a set. If you don't know what a type, and if you don't know what a set is, it's like a space. Huh? And if you don't know what a space is, it's like a type. So a field is a type supporting the following operations. Okay, one, addition, which we write using this equal armed cross as summary. Two, subtraction, which maybe you write using a hyphen, or if you are a typographer, maybe you know some better character to represent subtraction with, but anyway, that's what I know. Multiplication, which in programming we use asterisk, because I don't know why. And division, like slash, right? Okay. So you can add, you can subtract, you can multiply, you can divide. That's a field. It's a type supporting the following operations. And it turns out, if you take the numbers 0, take a prime p. Okay, so think in your head 17. Think about 17. Contemplate 17. If you take the numbers 0 up to 17 minus 1, 16, it turns out that is a field. In other words, that type, that data type, these points, we can define an addition, a subtraction, a multiplication, and a division in such a way that everything plays nice with each other. Okay? And what is it? Well, it's just operations, and then you take the remainder mod p. You know what I mean? Who knows what I mean? Taking the remainder, right? So let's do an example real quick. What is 3 times 6 in the field of integer, 0 up to 16? What is 3 times 6? 1. So in other words, 1/3 is equal to 6. That's another way of saying it, right? 1 divided by 3 is equal to 6. That's also how you would say that. Okay, but you see, so you do 6 times 3, that's 18. Take the remainder by 17, that's 1. So okay, that's how the operations work. Okay, we know. Who felt like they learned something just then? That's great. So, right, so that's that. In our situation, actually p is going to be a really big number. So like a number which is larger than the number of atoms in the universe, roughly, I think. So it'll be like 2 to the 256 or something. Okay, it's a big number. Yeah, or maybe even bigger. Right, so here's the thing to know about SNARKs. This is also something we won't touch this as much, but it's a good thing to know. In SNARKs, when you're programming SNARKs, when you're writing that computation that will be certified by the SNARK, the only efficient thing you can do is field operations: addition, multiplication, division, subtraction. Everything else has to be sort of simulated using those. And so what's most relevant for us is we're going to be doing stuff with hashing, okay? Stuff with hash functions. And our hash functions are going to operate on field elements. So you'll see this type, field.t, which refers to this type of field elements. And hash functions are going to eat it. Everything will work with field elements. So that's the extent, really, that you need to know about field elements. But just so you know. One last thing, and then we'll dive into actually doing some hacking. We'll taste the marshmallows of the 45 minutes of setup. Merkle trees. Who knows about Merkle trees? Who doesn't? Don't be shy. No one comes out of the birth canal knowing the sum total of human knowledge. OK. So let's just talk about that really quickly. Should I put? Oh, all right. Yeah, that's what I thought. So is there anyone who really wants these Docker commands to still be up here? Yes. OK. That's good. Sorry, I'm really not watching the time at all. 11:30, 11:33, we're going to 12. Yeah, OK. So look, here's the thing about Merkle trees. let's say I'm you, and I have some, well, or I'm me, and I have some data. And I want to tell you something about this data. Well, it's a lot of data. It's 4 things. I'm not going to tell you about 4 things. So I want some kind of succinct representation of this set of data in such a way that later I can talk about this set of data. Okay, so what I'm going to do, I take this data, I take it pairwise, so this one and adjacent neighbors, and I hash them together. These I hash, and I get some hash value. These I hash, and I get some hash value. Okay? Then what I do again, I take the next layer, there's half as many things, and I do it again. I take these together, I hash them. Okay? And now I get this one hash, which is kind of like a hash of this whole data. But it's a very structured hash. It's a hash which is the hash of 2 hashes, each of which is the hash of 2 hashes, each of which is the hash of 2 hashes, and so on and so on. And what this structure allows me to do is actually to prove to you membership in this initial set of values that I committed to. So I have this whole set here. You know, now it's a set. I have this set S of data. And I want to prove to you, let's say this was like 3. I want to prove to you that 3 is in S after I've sent you this initial hash. Anyone have any ideas of how to do this? Anyone who didn't know about Merkle trees before? No. OK, well, I'll tell you. Here's what you do. You say, OK, 3. I'm the guy proving. 3, cool. That's, no, 3's, I'm not going to put it there. I'm going to put it here. That's a little less boring. So 3 is the second thing here. So first I draw the path down to 3. Boop. Then what I do is I take the hashes, which are sort of hanging off of that path, always in the direction that I didn't go. You see what I mean? So I'm going to take this one, because that's in the direction that I didn't go. I went left at the top. So I'm going to take this one. And then I'm going to take this data. This leaf. But you can imagine, right, if this was a deeper tree, I would have gone left, right, left, right, left, 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 right, 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 and I would have given you a bunch of hashes all hanging off the side. People see what I mean? Yeah. And then what you do is, once I send you this data, you can sort of recompute for yourself what the root, which is implied by that data that I sent you. You can take, you know, all the data you start with 3. You say, OK, hash 3 together with that little thing I sent you. Then you have a hash here, this one. Then hash that other side hash on the right with what I sent you. And then you can check if it's equal to the original hash that I sent in the beginning of time. Makes sense, right? Or does it not? I don't know. I should ask, does it make sense? No. Who says no? I'm confused. Who's like, ugh. OK, what's confusing?
So are you just providing me the state root hash, or are you providing me these other hashes that I can recompute 3?
Yes. Well, you can't recompute 3. I'm going to send you the root of this whole set. And I'm going to send you, now I want to prove to you that 3 is actually in that set. So I'm going to send you 3, and I'm going to send you all these hashes hanging off the side. And then you can recompute, oh, what would the root be? And you can check if it's equal to the original thing. Does that kind of make sense? Yeah. All right, that's Merkle trees. Yay! Now we understand everything that we'll need to know. Everyone, you know, give yourself a pat on the back. Come on. OK. All right, great. That's good. So now it is time to taste the fruits of your labor. Go ahead and open up a terminal. Sorry. OK. Yep. So open up a terminal, like this one here. And if you haven't, who has run the Docker and it's running still in Bash or whatever? Who has not run the Docker? Because now it's time to run the Docker. So, oops. Oops. Don't look. Actually, you can look. Okay. So, all right. I don't know. This one? Oh. Uh-oh. Oh, yeah. Good idea. Oh. Okay, good idea. Oh, thank God. All right, so everyone should be in this situation. And go ahead and go into SFBW workshop, that directory. Cool. If you need a hand, does anyone need a hand? All right. Now, open up Visual Studio Code. Oh, there it is. Oh. Okay. So here we have Visual Studio Code. Now, I'm going to open the so-called command palette. You go, no. Does anyone know the so-called command palette in the view menu? And I'm going to type container, and I'm going to do attach to a running container. If you don't see this, you have to install the remote containers extension. OK? This is just for setting up editors now. OK, so attached to running container. I'm very lucky. There's one right here. I guess it got some automatical name. And I'm going to click that. Now I'm happy because now it made a new window, which is like, oops, which is running in the container, or it's sort of pointed. Actually, I have no idea how it works. But anyway, OK. Now once I'm here, everyone with me? Everyone able to do that? Attach to running container? Now I'm going to go File. Open folder. And I'm going to click on SF Blockchain Week Workshop. OK? And maybe, how about problems? Not, whatever. Just this one. Cool, it's like loading. Uh-oh. Oh, no. Oh. Maybe I just do it one more time. No, fuck. All right. Oh. Extension host agent is already running. Oh, it's probably because like I already did this before, and I like reattached or something like that. Let me just like kill the. Sorry. I think I added myself to the Docker group, which made it work before. So hopefully. Sorry, everyone. No. Fuck. Don't look. Is anyone's able to do this successfully? Oh, maybe that worked. Fuck.
Do you want to try swapping
Um,
the laptop or?
Okay, if people can just bear with me really quickly. Oh, you know what, actually? It's working for other people? Yeah? That's great, because I have it working locally, so I'm just going to work on my local copy of it without using Docker, but we went through the Docker thing, so. Okay, so. Going to go into solutions. We're gonna go talk about that hash preimage thing. Okay, so if you can, open up solutions/ex preimage .re. Okay? What's that? Yeah. So this is the program which represents that interaction before. So remember that slide with Alice and Bob, where Alice is able to send Bob the hash and then also prove to him that actually it is really a hash. That's what we're about to do in Snarky. So Snarky is a ReasonML DSL. ReasonML, it's like OCaml, but it looks kind of like JavaScript, so hopefully people are happy about it. Let's just walk through this file. It's going to accomplish exactly what we just described. So the first thing that we do is we have some boilerplate at the top. Okay? Cool? It's just some boilerplate. It's just importing basically the Snarky library. Cool? Below that, we have to declare what our statement is for the snark, or the public input. So these are two important words, statement and public input. They mean the same thing. It means the data that I'm going to reveal to you along with the snark. So in our case, it's going to be a single hash, right? I'm going to show you this hash, and I'm going to prove to you something about the hash. Does it make sense? So this is how we describe it. We kind of put this list thing, and we put the hash module inside of it. The next thing is basically declaring what is the top level private input, also known as a witness. So these are two other words which are interchangeable with one another. So I talked about, just so you have it in your mind, public input that's like the same thing as a statement. That's what I'm proving to you something about. That's what I show you. And you have the private input. That's what I'm proving. that I know, but without showing you. And that you could also call a witness. Cool? Because it witnesses the truth of the statement. That's the idea. So here what I'm trying to prove to you is that actually, this value is the hash of something. The witness is going to be that something. Make sense? The preimage of the hash function. The value which hashes to the public value. With me? Yeah? So, and it's just going to be a single field element, like a number, like we talked about. And now we're ready to define our snark. What we wanted to prove is, I know a value called preimage, such that if you were to hash preimage, it would be equal to the statement, aka public input, which is called h. So the way that we do that is by defining a main function. Main takes two things. It takes the witness, the private input, and the statement, the public input. And then it just sort of, it checks whatever property that we want to check, right? I want to basically prove to you, yeah, well, let's take a look at the definition of main. It's very simple. It's just saying, assert that these two things are equal as field elements, h and the hash of preimage. Straightforward, right? Can people read this okay? Do they understand? Who's like, what? Please say, I'm like, what? OK, yes, can you speak to your confusion? Because if it's your confusion, it's also probably someone else's.
So main is just a function, I guess. Am I reading that correctly?
Main, yes, sorry. So in terms of the syntax, right, so let is how you declare values and functions. So I'm saying define main, a function. It's going to be a function which takes preimage, witness, preimage, which has type witness, .t, and a hash h, and some dummy value, and then it's going to, be a function that sends that to this. This is the body. Does that make sense? Oops. So maybe we should have done some examples. So who's confused about the syntax? Raise your hand. OK, let's do a little syntax, just so people are comfortable. This is the crash course. And I'm going to, when we start coding, I'm going to link to a big cheat sheet. But here, we can get a feel for it. So here's how you define things. You say let, then the name of the thing. So a cool number equal 3, semicolon. Cool? Functions are like this. You put the arguments, and then you put an arrow, and then you put the body of the function. Make sense? And now we can look at the type of the function. And it's like, a cool function. That's a function that takes 2 ints and gives you an int. Make sense? Yeah?
How does it know they're ints?
Because I used addition on them. So it did type inference. Oops. One more thing. If you want to have a function with multiple lines, then it's like in JavaScript. You have curly braces. So you're like a more cool function. So it's going to take x and y, and then I put curly braces, and then I say let xy equal x times y. And then I return xy plus 213. Make sense? And I don't have to explicitly return anything. It's implicit. It's the last value. Make sense? All right. Now just so you know about arrays, lists, and strings, that's all you'll need to know about. So here's how you define a list. So here's some numbers. It's a list. And if I look at the type, it's like, yep, this is a list of ints. All right? Now there's also arrays, which are different from lists. You don't need to know how, but they are. So here's an array of strings. And the syntax for arrays is you put these the brackets, but then the pipe, the bar. So an array, so you put brackets and then a pipe, 1, 2, 3. So now it's an array. All right? Because then I put a pipe. Yeah?
What does the colon syntax mean on the next line?
That is how you ascribe a type to something. So here I'm saying other numbers has type list of integers, and it's this. Cool? It's not necessary, though, typically. Typically, the type can be inferred, right? Because here it's like an array. Yeah, that's an array of ints. Make sense? Cool. There's loops. So that looks like this, like for I in some int to some other int. And then you put curly braces, and you put the body of the loop. So here I'm saying like for I in 0 to however long the array of strings is, -1. Pick out the ith element of that array. Just this usual bracket syntax, on the array, indexing into the array. And then I do a printf. So I printf like this string has length, whatever. OK? Make sense? So who's like, OK, syntax, yeah, it's syntax. Yeah. So back to the example. So there's also modules, which are like, modules, like blocks of, like it's like a file, basically, like a module. You know what I mean? OK. So back to main. So main here, it's a function. It takes these 2 arguments, then it has to take this 1 dummy argument. Don't worry about it. And it returns, maybe it's like clear with curly braces. All it does is it makes an assertion. It says, oh, assert that these 2 things are equal. What? The hash of the preimage and h. OK? Does that make sense?
So there's no zk-SNARK yet. It's just like equating the preimage and the hash.
This is the computation that we're going to use SNARKs to prove.
OK.
So now what we're going to be able to do, and then we just call run main, and that's all we need to do. So now we're going to be able to use this to make SNARKs. Let's see, what's it complaining about? Oh, I didn't put a semicolon. All right. So, does anyone see my error?
Double semicolon on my point.
Thank you. Thank you. So what we're going to prove always is I know a first argument to the main function, so that if you evaluate main with that first argument and the second argument that we both know because it's public, then main will execute correctly with no assertion failures. Does that make sense? So that's what I'm proving to you. I'm proving to you that you can that I know some value to plug in here, so you can execute main. OK? So now let's see how we actually call this from JavaScript. It's really simple. So here I'm just like requiring some stuff. I need to, I start this like snarky instance. Now I'm going to prove to you, I'm going to send you like the hash of 5 basically, and I'm going to prove to you that actually that's the hash thing, but without revealing that my super secret number was 5. OK? So what do? I just call snarky.prove with an object that has statement. It's this, the hash. Witness, the preimage. Then I'm going to take the proof. It's a promise. Promises like JavaScript. Yeah, everyone knows JavaScript. No, who doesn't know what I'm talking about? It just means like after this is done, then do this. So then I'm going to take the proof. I'm going to print out the proof. We'll see how tiny it is. And then I'm going to verify the proof on that statement. Notice I'm not plugging the witness in here, right? That's going to verify it, tell me was it a good proof or not. And it's going to say, hey, did that actually verify? So now if we take this. So now let's run it. Sorry. This is the cool part, which is definitely going to work. Ooh. All right. So go into SFBW workshop, solutions, ex_preimage. Now run npm install. Cool. And now run node on index.js. That's that program that we just looked at over here. So, all right. So let's run the program. It's just building the snarky code. That's why it takes a sec. Ah! Don't look, don't look. It's because I changed some stuff. OK. Yep, cool. So it said, cool, I made the proof. It's this big mess of data. I promise you it could even be smaller if it wasn't base 68 or whatever this is encoded, base 54 encoded. And it says, was the proof verified? True. Cool. So now let's try and like be evil, right? Now we're going to be an adversary. And we're going to be like, ha ha ha. I'm going to convince you that some other thing is a hash. So what I'm going to do, I'm going to come here and I'm going to be like, oh, yeah, the statement, no, not that hash value. I'm going to try and convince you that like, actually, I know that like 100 is actually the output of this hash function. Okay, I'm lying to you, right? I'm going to try and convince you. Let's see what happens. Yeah.
So the proof is not deterministic, is it? Because my output there is different.
Yes, it's randomized. Yeah. So, OK. Let's see if it works. Oh, no. It probably like killed the process or something. Anyway, it didn't verify. Probably that's what happened, right? I'm not sure.
I think it went to a different promise, probably. The catch promise.
Oh, it goes into the catch thing. OK. It threw an error or something. Anyway, rest assured, it did not verify. This JavaScript API is a little new, so you're very lucky. You get to experience cutting-edge technology. OK, so let's see, just make sure.
Sorry, did we have to make a change to index.js to run? Or if I just clone the repo, I can just run node on index?
Yeah, it should work, yeah. Oh, you have to do npm install, but then it should work.
npm install and npm run build, and then index will work.
You can also just run index, but yeah. It'll recall into Dune. What's up? What is it? So basically what happens, here, let me just explain how the whole build works. So like we wrote this file, right? This like snarky program. What happens is this gets built secretly to snarky, like to the this exe file. Huh? Oh, I don't know. Yeah, I don't know. It's like an OCaml. Yeah. So that's what it gets built to, and then this is like a little. It's like a little. You know, it's spawning that process and it's communicating with it to get it to prove things and check proofs. Okay. Make sense? Yeah. This is just like a hand. This OCaml process, talking to it and like telling it to produce proofs and stuff by giving. Huh?
What is the input spec that is used?
This input spec. Yeah. This is how you define what is the input to your snark.
So this is special for snarking?
Yes. All right. Cool. Very good.
So how do we play with that? How we modify some number?
Yeah. Let's do the following thing real quickly. Let's change our snark a little bit. Here's what we're going to do. I'm now going to convince you I know not just any number which hashes to this value, but I know an even number which hashes to this value. OK? People see what I'm saying? So like before I was like, yeah, it's like the hash of something. But now I'm going to tell you something a little more complicated. It's the hash of something which is even. OK? People with me? So here's how we're going to do that. All right. So if I were you, what I would do is I'd be like, oh, OK, even, like, probably I'm going to like use this field module somehow. A module is like a collection of functions. Make sense? Yeah. Yeah.
Are you asking for the next line?
Oh, yeah, do you know?
Field of a spec,
So with the function we have, I'll tell you what we're going to do. We're going to convert into bits. Yeah, if I don't have like mod 2 implemented and stuff, but that would be a good way to do it. But so what I'm going to do is I'm going to take my field element. I'm going to convert it into bits by using this 2 bits function. So I can go like field dot like whatever, like, oh, 2 bits. OK. That's going to like, it takes an optional length argument, which is an int, and it's going to give me like an array of bools. That's how to read this type. So I'm not going to even pass the length. So I'll be like, OK, field dot 2 bits on preimage. OK, cool. Now I got some bits. And now I'm going to say the 0th bit is what? How do I, is the 0th bit is false. Yeah, or yeah, right? The 0th bit is 0, basically, right? That's how I say that a number is even. Make sense? So I'm going to say, so this is a bool, because it's a bool array. So I'm going to say bool.assert false that. OK? Cool. So you need to delete your proving key and your verification key when you change the function. Oh, yeah, we'll talk about that in a second. But now let me rerun this. And it's not going to work because we did like #5 or something. So I try and run it. It's like, no, it didn't work. And the reason it didn't work is because we put this constraint on evenness. And the value that we were using as the preimage was 5, which, as we all know, is not an even number. Correct? But on the other hand, if I change this to, I don't know, 50. Oh, is that 50? 50. Now let me rerun it. And it works. So now I proved to you that actually I know an even number. Make sense? An even number which hashes to, sorry. So I'm proving to you that I know an even number which hashes to this value here.
Can you start the program again from the snarky program?
Yes. So what I added was I convert the field element into bits, and then I assert that the 0th bit is false, or 0. Make sense?
So in this case, you prove 2 things, right?
Yep.
Even number, and then another one is the hash.
Exactly. Cool? Yes.
So this snarky.proof stuff, so that you do like locally in secret, I guess, to create this proof,
Exactly.
and then share publicly the statement and the proof.
Exactly. So like, imagine like, yeah, this is like on my computer, and then I'm going to send you statement and proof, and you can check that on your computer without me having to reveal this witness value to you.
Someone have to write the exact same, so you send them your like preimage dot reason file as well. Like would they have to just like write the exact same steps, or like would they?
You would send them this program as well. Yeah.
So this is one way to solve it, right? So like, how do you, so you are, I'm the prover and you are verifier, and what input that you receive and what input that give you in this case?
So you're the prover, I'm the verifier. Oh. So you're going to have the statement and the witness. Oops. The witness is the preimage to the hash function, the even preimage, right? So you're going to have the statement, which is the hash, and the preimage, which is that even number which hashes to that value. That's what the prover will have. And the verifier will just have the statement. Then you're the prover, you produce a proof, you send it to me, the verifier, and along with the statement. So I just have the statement and the proof, and then I check the proof against the statement.
How does the verifier, how does he have statement? Each statement requires preimage.
So like you're the prover, you run this program, this is the statement. You see? Huh? It's just like this, it's just like a blob of data. And then you just send me this, and you send me this proof, and I can check it. Does that make sense? Yep.
So how do I judge the black box snacky?
Say that again?
So snacky is a black box, right?
Yes.
So how do I judge the black box?
How do you do what? Judge it?
Trust.
Oh, trust it. You can look at the source code. It's not a black box.
How does the verifier know that this blob of data you send as a statement, that it's actually a statement in the state that it's a hash function?
Excellent question, which brings us to these files that I kind of wanted to ignore, but which are this proving key and this verification key files. OK, so when you make a snark, we'll talk about this in more depth after lunch. But there's a couple kinds of snarks. Who heard about trusted setup? It's famous, right? So there's snarks which require a setup, and there's snarks which do not require a setup. Of snarks which require a setup, which is what we're using now, after you write your program that you want to snarkify, you have to perform this setup to obtain a proving key and a verification key. Now, to anyone who you want to be able to create a proof, you send them the proving key. To anyone you want to be able to check a proof, you send the verification key, and you go from there. So that's how it works. Did that answer your question? It was you, right? It's because this verification key, burned into it is this whole hashing computation. It's burned into it. Does that make sense?
Is the verification key the one you were supposed to get rid of?
I had to delete it when I changed the program, I think. Huh?
So how do you redo it?
How do I do what?
Redo it once you change this thing? So you did something where you cleared out.
I think I deleted the verification key and the proving key when I got some nasty C++ error. And then it just probably made new ones, yeah.
Verification key is what people refer to when they say that toxic jump or something.
So the toxic waste, so here's about the toxic waste. In generating the proving key and the verification key, I generate some secret randomness that I can't tell anyone. And if maybe you were like listening to my laptop with like a stethoscope or whatever, I don't know how it works, you can maybe like get those bits. But they're not in the proving key, they're not in the verification key. They're just something that I need to create both keys. That's a toxic waste, and it gets deleted. You know, it's inside the memory of that running program, and then when it doesn't ever get written to disk or anything.
So I modified the program with the array code, and I run again. The problem is that even if I clean it, it runs true all the time. Wherever it fits 5, it fits. Probably
Well, yeah, that's because you're proving, because we put as the statement the hash of that value, so it will always work. If you change the statement to some other crap, then it won't work.
No, probably the other reason. I was not saving.
Oh, okay, maybe, okay. Cool. So, does everyone feel like, okay, snarks, maybe not so bad? No. Who's like, oh, snarks, like just as bad as I thought? Who's like, snarks, maybe a little bit better than I thought? Okay, well, that's progress. We have a whole afternoon, so we'll get there. All right, so now we'll break for lunch.
Yeah. We have one announcement first.
We have one announcement. Let me also take a quick poll. Who is like, yeah, I really want to understand, like, I heard there's all these different kinds of snarks, like setup, no setup, like, what's the deal? Who would like to understand that a little better? Okay. All right.
Okay, cool. So we're going to break for lunch in a second, and then if everybody could be back like around 12:50 or 12:55, all the food is in here. If you had a dietary restriction and you're not finding something in the provided catering, please come and see me, and we'll make sure that you're taken care of. There were a lot of permutations, and I'm just unsure about a few of them. So no worries, though. We'll get you taken care of. And then, can you hold this, SC? Thank you. Yeah, so we also just wanted to have some fun. We asked you guys to jump over a couple hurdles in the registration, explaining what zero knowledge was in 3 sentences. So we kind of love when people are able to do it in a really easy to understand way or kind of a fun way. So we're giving some of the participants some cool coda hats if we liked your response. And Christine and I picked these out. So yeah, hopefully we'll have some fun. So the first response, I'm not going to read all of it, but this guy said they seem like magic, but they're real. So that's a cool response. Eric McCarthy, do you want to get your hat? Yeah. Okay, awesome. And then the next one, somebody said, I can use ZKPs to convince you that I've correctly run some potentially very complex computation without you needing to run the computation yourself and without you learning anything about the data I've used in that computation. Great response. That was Bobbin. So thanks, Bobbin. And then another response from Ariel. Hopefully I'm saying that right. Said method by which one person can prove to another that they know some piece of information without actually disclosing what the information is. Cool, back there. Awesome. So thank you guys again for jumping through those hurdles. We kind of wanted to make sure everybody was like down to dig into SNARKs and not just signing up for the free breakfast. So yeah, thanks. Enjoy lunch.
Let me just say one more thing. So after lunch, I'll do a little thing on what are all the SNARKs, like what's the deal, and we're going to dive into what are some cool applications to get you re-excited after. It's like we gotta hype it up, It's like you do some coding, you're like, hard, and then we have to create some excitement. We'll look at some applications, imagine all the amazing possibilities, and then there's some exercises that you can work on, and it'll be fun. Okay. I am happy to see everyone still here. Is everyone good? Like have a little snack, coffee? Yeah? Oh yeah, 1 second.
So we really try hard to avoid wasting food, so we don't order a ton extra. I understand sometimes that means there's a few people who don't get a sandwich if you don't go over and get it. Can you just raise your hand and let me know if you did not get something to eat? Okay, so there's 1, 2, 3 people. I do have some extra food coming, so I'll just come and put it on your seat, and the rest will be at the back. I just ask if you did eat lunch, please don't go and eat the extras. Just give the people who didn't have their lunch a chance to go grab something. Thanks.
Cool. So, here's what I'm thinking. There are a whole bunch of exercises for people to do. But maybe that's not the most effective use of time. I don't know. I want to try and give people as much information as possible, right, in the limited amount of time we have. So I think we'll do some exercises, but I'm going to inject some more content, so to speak, that I wasn't planning on talking about, but I think is useful and important enough that I should talk about. Are people on board for that? All right. Excuse me. So, sorry. There's basically 2 things that I want to get into before we, look at the exercises. They are the following. I want to talk about some applications to give people some idea of what's possible to, open a vista, so to speak, for people. And then I want to talk a little bit about the sort of ever-changing landscape of SNARK constructions. And then we'll do exercises and get a little more hands-on experience. Does that sound good? Excellent. So let's talk about some applications. So so we have Alice and Bob. I really love, I don't know, I love this Alice and Bob. This is a good Alice and Bob for me. Where's the cursor? Okay. So, sorry? What's the problem? The wrong plants. What's wrong with the plants? I don't get it. Oh, yes. Too true. Well, she sends him hash, right? So, okay. All right. Come on. It's off the cuff. All right, so let's go back to this voting application. Let's understand kind of how we had an idea, right? We did this. Now we know. Now whoever didn't know before, now you know the stupid preimage example, right? We all know, right? Proving I know some value that hashes is something, right? But like, okay, let's talk about something real. So back to this voting thing. Who remembers? Everyone who doesn't remember the voting idea? We all remember, right? Anonymous voting. That's it. Yep. So here's how it's going to work. There's going to be a registrar. That's going to be a central party. Note, you could replace it with a blockchain if you really wanted to go like full decentralization, but that's not how we're going to implement it today. There's going to be a registrar that's a central party. People come to the registrar and register. That's what the registrar is for registering voters, okay? So you're a new voter, you come to the registrar, you say, hey, yeah, I'm actually a member of this organization. You have some rule by which you can decide whether people are members of an organization. For now, let's just say we sort of know who the set of people are, okay? Who are the members, and then we can figure out later how to take care of that if we want to fix it. You're going to come to the registrar, give them basically some kind of public key, some kind of record, identifying record. Then later, registered voters are going to be able to vote on whatever elections they want. They're going to be able to create new elections and so on. The security desiderata, this is a Latin word. It means desired things, are two. One, registered users can vote exactly once on every election. Fair enough? Moreover, users who have not registered cannot vote. Okay. Second of all, votes should be completely private. In other words, when I publish my vote, there should be no accompanying information, identifying information accompanying it. All right? So a little more how it's going to look. This is the registrar. It's some horrible, dark government bureaucracy building. This is the voter. There are many voters. As I said, they're going to first register the voter record. Then all the voters are going to submit their votes. And the registrar will rebroadcast all those votes to everyone, okay? And remember, each vote has no identifying information. And this could be replaced with a blockchain. You could use a blockchain instead of this, but we're not going to. Okay, but so it's with the centralized party, but it's not necessary. You could replace it with a blockchain. Okay, so let's kind of design an architecture. So here's like a simplest possible version. Okay, maybe I write down also my favorite color. So here's my voter record. Okay, I write down my voter record. Here's my name. Here's my favorite color. It's blue. Here's my private key. It's some bytes, and I send that to the registrar.
You have to give your private key?
No, this is a naive version. And then we'll fix it bit by bit using the magic of SNARKs. Yes, you correctly point out that's not good, right? So okay, so everyone sends their voter records. At the end, there's 4. I don't know. I accidentally animated this. The registrar has these 4 voter records, let's say, and registration is closed. Again, you could do it with open registration. It's just a little more complicated, so I'm not going to talk about it. Then when I want to vote, I send the registrar the name of the election. In this case, it's ketchup is good. Kind of a controversial topic. Like, let's take a poll. We'll reveal our votes. Who thinks ketchup is good? Who thinks ketchup is not good? Some people think ketchup is not good. That's the name of the election. I'll send my private key. Obviously, this is still silly, right? I'm not going to be sending my private key. That's very identifying information. And I'm going to send my vote. Yes. What is the registrar? Social Security? Yeah. Everyone send me your Social Security, mother's maiden name. The registrar is going to check, first of all, does this key belong to a registered voter, right? Because we only want registered people to be able to vote. And second of all, has this key voted in this election yet? Because we want everyone to vote exactly once. And the registrar is going to keep a tally. Okay? That's obviously not a privacy-preserving version. Yes? The registrar sees everything. They know everything about how everyone votes. So how to fix this. Right. As I said, the registrar can see how individuals are voting. Moreover, people are just sending their private keys on the network. So like, is it really a private key? It's really not. Not good. So here's how it's going to work instead. Instead of this whole record of data, when I register to vote, just send a hash of it. OK? Make sense? Now it's blurry. You can't see it. It's just a hash. That's how I register. I just send you this hash. Boop. Meaningless, right? Completely meaningless. Now, when I vote, before I needed to prove somehow. I needed to prove somehow that I was really a registered voter. How did I do it? I sent my private key, and I said, oh yeah, it's my private key. You look it up in the list. I'm there. I'm a registered voter. OK, here's what we're going to do instead. When you vote, instead of sending your private key along with the election, you send a hash of this data. The name of the election, ketchup is good, along with your private key. You're just going to send a hash of that. And the way to think about this, oh yeah, it's blurry. That means it's a hash. And the way to think about this is like a, think about it. This was a deterministic value, right? From your private key and from the election, this is the only thing you could compute is this one thing, right? You know what I'm saying? There's no freedom here. It's deterministic, right, how this is computed. So somehow this is like a unique, it's like a unique ballot for your vote in this election. You see what I mean? And on the other hand, if you show it to people, it wouldn't matter because it reveals, well, you really need to put some randomness in here, but whatever, but basically it reveals nothing about your private key, right? If you just publish this hash value, right? On the other hand, it's still determined uniquely. So it's somehow a unique identifying piece of information for you in this election. And that's how we're going to fix this problem. That's how we're going to address the problem of making it so that people can't vote more than once. When you vote, you're also going to publish this ballot. This little, it's like a torn ticket stub. You know what I mean? Along with your vote. So you're going to publish this, and you're going to publish your vote in the clear. Yes. Now, right. And with the snark, we can selectively reveal some information, namely this is really a hash, right? OK, but, and even more, we can say this is really a hash of the election is good, or sorry, ketchup is good, with some private key. OK, so I release this piece of data, and I prove to you, yes, this is really that deterministic piece of data that I only had one option of computing. That's how we are going to prevent people from voting more than once in an election. Does it make sense? And you called this is basically like how Zcash works. Don't think about that too much. And if you ever read about how Zcash works, they call this piece of data, they call it a nullifier. If you ever read about how Zcash works. It's this little torn ticket stub, You see what I mean with torn ticket stub? Kind of, maybe. OK. But there's still sort of an right. So that solves the problem of no double voting because this is sort of there's only one way I can compute this. But there is a remaining problem. How you told me, oh yeah, this is the hash of ketchup is good with some private key. But how do we know that that some private key is one that belongs to a registered voter? How do we know that? We don't, right? It's just something, yeah? So I didn't make a slide for this, but here's how. Maybe I think I made a slide for part of this. Hold on. Well, anyway, it's Merkle trees. OK, but the question is there a slide? OK, there's not a slide, or it seems to have disappeared. But yes, Merkle trees. So what do I mean by that? for some reason this keeps coming up over here. You know what? Let me mirror this, so that will save us all a little bit of time. Great. Yeah, okay. So Merkle trees. So what do I mean? Well, by now everyone has the Wi-Fi, right? And if not, just be like, hey, don't erase. Okay. So the registrar, they collect up all the votes, all the ballots rather, all the voter records, right? Which are, remember, are hashes of everyone's information. So this is like hash of Izaak with my private key, hash of Joseph with his private key, and so on. Okay. Then what they do is they build a Merkle tree. Remember Merkle tree from this morning? Okay. And they publish this guy. They publish the root. Everyone knows the root of the Merkle tree. They throw it to the winds. Have you heard the root of the Merkle tree is 0x5517, whatever. They tell everyone the root of the Merkle tree. Then, that represents the whole set of registered voters, right? Then what you do in your SNARK is you say, there is someone in this Merkle tree. I know, remember Merkle proof? I can prove membership in the set. I know some registered voter which is really in this set. And if you take the private key of that registered voter and compute this value, hash of that private key with election is good, with ketchup is good, you get this torn ticket stub value. Does that make sense? And you publish that proof. So what you're basically saying is, yes, I'm a registered voter, and moreover, if you take my voter record and hash my private key with ketchup is good, you get this public value, my torn ticket stub. Does that make sense? Kinda? Who's like, okay. Okay. Well,
Wait. The problem for me is you just switched, right? If I understood correctly, when you were drawing that tree, you were doing it from the perspective of the voter department, who is basically going to receive some hash from a voter, and you want to verify that that voter is inside of the tree. Is that what you're saying?
yes.
Then you switched all of a sudden that last sentence to say, hey, I'm a voter, I'm going to send you my ticket stub. So
Oh, yes. Okay, sorry. So let me correct a little bit. Not only do I publish say the root, but maybe I publish this whole tree. Okay, so everyone has the whole tree. Okay?
Specify what exactly are the leaves of that Merkle tree?
Each leaf of the Merkle tree is a hash. Is the hash of the registration record. Make sense? But hashed. Cool? And then we fully worked out this example and the code's online, so you can look at it. But basically, I'm a voter. Here's what I do. It's what I just said, right? I take the path in the Merkle tree that corresponds to me, and I make a snark saying, I know someone in the Merkle tree, so that if you open the Merkle tree, take the private key from that person, and compute its hash with ketchup is good, you get this. Yes?
So, just out of curiosity, when you're using this word private key, but really are we talking about, let's say, some ID that would be assigned to each voter by the voter registration, by the voter department?
No. It's random bytes that you sampled yourself.
And I do or I don't provide that? I do when I register. I never provide that to the voter department anymore.
No. You only send them the hash of all your data. So like, here's your private key, but you never showed them this record.
So the tree was built during registration.
Correct.
And what we're talking about is the verification during the actual voting process.
Yes, we're talking now about voting.
Do I know the path of my
Yeah, so like, let's say, for example, that the whole tree is public, and you know what the hash of your voter record is, so you can just look, oh, this one's me. Make sense? Oh, sorry, I keep forgetting to repeat questions just for people who are watching at home. Someone just asked, oh, do I know, how do I know like which one's me in the tree? And I answered, and then before that it was asked something, oh, I can't remember anymore. Anyway.
Can I ask, is this tree constructed after everybody's voted?
Is this tree constructed after everybody's voted? Yes.
No, after it was registered.
After everyone's registered, I'm sorry, yes. We have a registration period, everyone registers, then we close registration, then we construct the tree. But you could do it in a rolling way, it's just more complicated.
And the tree is constructed, though, by the registrar, and they have centrally distributed broadcast.
Yes. We could do it with a blockchain.
Okay,
But
so
yeah.
there was a time when the registrar never had the private key, so the user has sent this hash of the private key,
To the registrar.
the election to the registrar, and how did the registrar know? I guess they just used AI.
Yeah, or they know, like maybe everyone came in person and they gave them their hash or something.
Okay.
But you could have rules, right? I mean, like for example, you could create an organization and you could say, oh, if you get a signature from, 3 of the people in the organization, then you get to join the organization. You could do it in a more distributed way as well. Sybil? That's not within the scope of this, correct? Yeah. The question was like, how do you prevent like Sybil attacks? And that's, I'm imagining like a closed situation where like the registrar knows everyone. Yes? How do you map a hash of the user information to? How do you link them? Yes, so the SNARK lets you link them. So the question was, how do you link together the hash of your voter record, which you submit when you register, with like the hash, this torn ticket stub hash that I keep calling, with the election. You make a SNARK which says, yeah, if you go in the tree and take my hash there, I know how to open that up. I know a preimage of that hash. And then if you take that preimage, one of the fields in that record of data will be my private key. And then if you extract that and hash it together with ketchup is good, then you get this public value that I'm telling you about. And so if we look at the code, let me just open it up just to give people an idea. Just maybe it will demystify it. Where is it? Oh, examples. So skip all that. Okay. Oh, I did something a little more complicated, like with attributes. We can just skip that part. At the end of the day, this is basically what our SNARK is going to do. The public input will be like the voter record and the Merkle proof. Or sorry, the witness will be the voter record and the Merkle proof. The public input is going to be like the root of the Merkle tree. That torn ticket stub, which is what I call a nullifier. Okay? And yeah, some other stuff, don't worry. And oh, and the election ID, and then some attribute stuff. Don't worry about this part. Just think about the election ID, the Merkle root, the nullifier. Election ID, Merkle root, nullifier. What I'm going to prove is, hey, if you take that voter record and you hash it, then then it's the case that this is a Merkle proof of the membership of that hash in the Merkle root. Moreover, if you then take that voter, extract the private key value from that record of data, and hash that together with the election ID, then that is equal to the nullifier. which is the public input. Okay? Does that make sense? Roughly? That's what I said. Does that make sense, Tony? Yeah.
But how can you, oh, never mind. This is actually, you're referring to the private key because this is something that's going to be handed off to the voters to construct.
The voter will run this program themselves. Yeah, this is how the voter proves. It's part of the secret witness.
Yeah.
The voter record, and they can pull out their own private key. Make sense? Well, I mean, yeah, it kind of does, right? Because like, let's say you're the registrar, right? So I come to you and I'm like, yep, like I'm Izaak, like, and you're like, cool, you're like number 2 in the Merkle tree, right? Then when I come back, I don't want to be like, yeah, I'm the number 2 guy in the Merkle tree, because you know who I am. You know what I'm saying? People with me? Yeah. Because the registrar knows how identities map to positions in the Merkle tree. Cool?
But when you prove that you need to give them the path, right?
Yeah.
So this means that like the registrar, they know who are you.
Well, no. Let's say that the registrar like serves this whole tree, so you can download the whole tree, and they don't know, you know, and then you pick out your own path from the tree. So the question was like, oh, the registrar like gives you the path, but let's say they don't. Let's say they give you the whole tree. Okay? Does it make sense? Not so bad, right? Pretty simple application. Who's like, yeah, that kind of makes sense? Who's like, I don't know. I have a question, and I want to ask it because probably other people have the same question, and it would be enlightening for everyone if I were to ask it.
This is, you're creating the proof and the statement. Sorry.
So like all this data here is part of the statement, and this is the witness, and we can run this to get a proof against this statement.
I guess I'm just confused because the last time we did main, that was the verifying function in our other example, right? Or am I? It still is. You're doing the same thing on 85 and 94 as you were doing the other function. Not the same statements, but we're still doing verification. Right. Where we did like field on. Oh, okay.
Was this just, you explain how at this proof, or this first one, you would establish that somebody double voted?
Yes. So how are you going to double vote? Well, every time you vote, you need to publish the hash of your private key with the ID of the election. You only have one private key. In any given election, you know, you compute this value in a deterministic way from the name of the election. You hash it together with your private key. So if someone sees, hey, this guy tried to, you know, this person tried to publish that same torn ticket stub with 2 different votes, then you can say, no, that's not okay. Do you see what I mean? This nullifier, this torn ticket stub value is public, and as you're eating votes, as you're checking votes, you're seeing these nullifiers flow in. And if you see a duplicate, you're like, no, that's a duplicate vote. Does that make sense? Smart, right? I didn't come up with that, so I'm not saying I'm smart. Yeah.
Did you say earlier that there's something along the lines of the SNARK proof, you know, when you're voting, it reveals the election ID?
The SNARK proof of reveals the election ID. Yes. The election ID is going to be part of the public input, aka the statement. So
yeah, when you're voting, you're sent the hash of the election ID and your private key.
and you also send the election ID.
Oh, okay.
So this is the public input. So the question was, well, perhaps it was answered. You send the election ID when you vote. Yes?
I just want to check my understanding here. Does that mean that, so suppose that I am the central authority that's collecting these votes?
Yes.
And everybody's voting on the election. Ketchup is could hypothetically do if the set of voters is very small that I could basically like rainbow attack to understand like, you know, you're giving me a nullifier and I'm going to say, okay, let me first like just trial and error, see like, are you this private key, are you this private key, so on.
Well, you don't know the private keys.
Oh, okay.
Yeah.
The central authority only knows the Merkle groups. Is that correct?
They know the hash of everyone's voter records. They don't know the contents of their voter records.
Okay.
Okay? Yes. The question was like, if I'm the registrar, sorry, just please watch this video in reverse when you watch this video. That's me speaking backwards. No. If the question was about like, oh, can't the registrar just like, you know, try everything and like see whose nullifiers belong to who? And the answer is no, they can't because they don't know the private keys. Yes.
Can we look at your diagram?
Let me just add one thing. The real answer is like you're supposed to like put more randomness in the commitment. But I didn't want to talk about that.
In your diagram of the voting, in your presentation. So in addition to the hash, they do send election ID unmasked.
Yes.
That's what you're saying.
Yes.
Yeah. So I think in this diagram it would help to show those two pieces.
Yes. Sorry. Yes. Yes.
Okay. If you didn't, is it possible for the SNARK to actually just reveal or prove that the election ID is, say, election ID 100?
You're saying like reveal only some information about the election ID?
Or the full election ID. But my question is, do you send election first part of the SNARK?
Well, so you send it separately, but you know it verifies against the SNARK. So it's part of the statement. You know, remember before we had the statement and the proof and the witness?
Yeah.
So you send
your. Okay. Yeah. Yes. So you send it. Yeah.
Right. You send it. It's part of the statement.
So the SNARK verifies that the election ID of inside the hash matches the thing that you publicly sent.
Exactly.
Okay.
Exactly.
The second thing that the SNARK proves.
So sorry, just to repeat, you were saying the SNARK verifies that the election ID inside the hash is the same as what you publish publicly. Yes.
Okay. And then the SNARK proves two things, and then the second thing it proves is the membership in the Merkle tree.
Yes. The second thing it proves is the membership in the Merkle tree of your private key. Yes.
Okay, got it. Yeah, just making sure that those are two things the SNARK proves.
Yes. Exactly. Those are the two things.
Okay, thanks.
And SNARKs are really flexible. So now is where you can let your imagination run wild. You could also say, I want to have an election where only people who are over 30 can vote. Or I want to have an election where only people whose name is Izaak can vote. Or I want to have an election, and do you see? And then they would expose, yes, I am some guy, I am some person in this tree, you know, and assert that name equals Izaak, or whatever. You see what I'm saying? You see what I mean? Or assert that age is greater than 30. Yes?
Is there like an arbitrary set of computation that can be a part of the like proof function, or is there only like certain, like can you for instance like do like exponentiation or can you not do that?
Great question. So at the end of the day, remember what I said. Everything has to boil down into basically addition, subtraction, multiplication, division. So the question was, can you do anything inside of the proof function, or can it only be certain things? At the end of the day, everything has to boil down to addition, multiplication, subtraction, and division. Lucky for us, that's a universal set of computations. Any computation in principle can be reduced to those things. Now, there's often a world of difference between what can be done in principle and what can be done, you know, in the world. So there are some things which are more efficiently done than others. Now is a good opportunity to just point you at this page. If you go to codaprotocol.com/doc/snarks, okay, and then go to Getting Started with Snarky, and then go to, well, this is an example application, but Snarky Universe Library, which is what we have. Here is like the standard library, what is exposed to you. So you see you have stuff for doing field stuff. You can do operations. You can take square root, blah, blah, blah. Bool stuff. You can take and, you can check if they're equal, blah, blah, blah. You can peruse this at your leisure. You can hash things. You have this hash module, which I use. You have this Merkle membership proof thing. You have, you can do stuff with integers. So like, if you can make integers, you can do comparisons on integers. You can turn them into bits and stuff. There's Schnorr signatures, like an implementation of Schnorr signatures. If you want to do stuff with signature schemes, you can like check a signature. This takes a public key, a signature, and an array of field elements, and gives you a Boolean. Okay, so here built in are all sorts of useful functionalities that this is usually all you really need when you're making an application. Is like, for most applications, I think basically like Merkle trees, hashing, signatures, maybe some integer stuff, and it's predefined. But this all boils down to doing multiplications and additions in the field.
So previously you said in order to not leak the Merkle path, so user have to download the whole Merkle tree. Let's say if the voting system is for the whole country, does that mean everybody has to download the whole Merkle tree?
Yes, it's not a realistic proposal. Here would be a better proposal. So there's this registration period, right? And when you register, I also send you your Merkle path. Or sorry. 3 periods. First, registration. So everyone registers. Then we finalize the Merkle tree. Okay? And we compute the root. Then it's Merkle path time. Now everyone comes back to me and they're like, hey, give me this Merkle path. And then I just send you that Merkle path.
And you can record it at this time.
Yes, but then, so that's Merkle path time. First registration time, we make the Merkle tree. Then it stops, so it's a fixed Merkle tree. Now it's Merkle path time. Everyone comes back. I'm like, yep, you're number 3, you're number 17. You're number 71, blah, blah, blah. I know everyone. Then Merkle path time is over. Then it's voting time, and now it's fine. You see what I'm saying? You can just use that Merkle path, but you don't leak it now when you vote.
But you know my path.
I know your path. I know who you are. I know which index in the Merkle tree is you. But when you vote, you don't reveal who you are. You don't reveal which index in the Merkle tree is you. Yes. The question was like, isn't it impractical to send everyone the whole Merkle tree? And the answer was you don't have to.
You're sending people the path, or you're sending people the sibling, and then...
That's what I mean by the path, yeah. The sibling, that like thing that I drew over here with you go left, you go right, you pick the other one.
They need to make the proof.
Exactly. Excellent. Great. So now maybe some gears are turning in people's heads. Oh yeah, okay, I can see what I can sort of build. Let me tell you some other cool applications, just maybe to juice your imagination. Another thing that you can imagine, who knows about like, maybe you wanted to make some kind of network, okay? Like a Facebook, so to speak. But when someone accessed someone else's page, you didn't want to give any information about who you are, but merely that you are authenticated to look at their page, right? So like, it's very similar to the voting example, okay? So you'll see like this simple pattern is quite useful. So if I can give you 2 instances of this pattern, you can interpolate and understand the whole pattern, okay? So I'm me, all right? Here's what I do. I don't even need to redraw the image. I take all my friends, and I build them into a Merkle tree. And for each friend, maybe I store like, what is the friendship level as an integer or something, right? Like, are we super good friends? Or some permissions, some complicated permissions. Like, this person is only allowed to see my page on Tuesdays, or something, right? For example, okay? And now, and everyone knows the Merkle root of my friends database. And now, you talk to me and you're like, hey, yeah, like, let me see your page. But I'm like, oh, okay, like I don't know you. So you prove to me, oh, I'm one of your friends who's allowed to see your page on Tuesdays. And I check, is it Tuesday? Well, no, so I'm sorry. But if it were Tuesday, or if you were one of my friends who's allowed to see my page on Wednesday, then you would give me a proof attesting to that while not revealing anything else about who you are, because it's zk. This is your knowledge. So it would just show you that you're one of my friends who's allowed to see my, in my Merkle tree of friends, who's allowed to see my page on Wednesday, but I don't know anything about who you are. Okay? Does that make sense? Kind of cool, right? And you can sort of maybe see where what other kinds of things you could imagine building using this. Okay? People with me? Someone? Yeah. Questions about that?
There's usually just one verifier in all of these things.
Well, for example, in the voting case, probably everyone would want to verify, right? Like everyone wants to verify everyone's votes to make sure that the whole election went well.
And it's fast, verification is fast enough to make that feasible.
Oh yeah, verification is very fast. So just verifying single proof like one-off is like 10 milliseconds. And batching, you can do batch verify and it's even faster. So verification is fast, don't worry about it. Probably. And if it's not, then you can do proof composition, but we won't talk about that. Cool. One more class of applications that I want to convey really quickly. And this, so we mostly talked about privacy, right? We mostly talked so far about zero knowledge, right? But also useful is the succinctness. The fact that these proofs are, as we just said, fast to verify and really small. So let me give you an example. I have some slides. Maybe I can pull them up. It's in another slideshow, but everyone can see it, right? Everything. Maybe if I click this. Oh yeah, this is okay. It's kind of silly, but this is tongue-in-cheek. Okay, this is another class of examples. There's a problem in the world, which is that very often lenders make racist loan determinations. Who's familiar with this issue? You know, there's lenders online, and they very often are racist. Okay, big surprise, right? So on the other hand, like you wouldn't want to put the bar. You could say like, yeah, we can make the loan. We could check that they were being honest and using like some kind of somehow we believe non-racist procedure for determining loan worthiness. We could do that by maybe like putting the computation on a public blockchain. But come on, we're going to put people's financial information on a public blockchain? Ridiculous. So what you could do instead is basically have the lender, you have users like say commit to their data or something, I don't know, on a public blockchain, whatever. And you have the lender commit to like a loan policy. It's going to be some program which will take the user's data and check whether they deserve a loan or not. Okay? Make sense? And let's say everyone has inspected this program that determines loan worthiness, or maybe someone you trust has inspected this program and you believe it. Okay? You know the program. It's fixed. Now, but like maybe the lender doesn't want this program to be public. Okay, they can keep it private if they want. Now, what you do, okay, you don't really have to, don't look at those because they're a little more specific, but basically, you're on your website, you make a request to the lender, you're like, hey, yeah, like here's my data, let me know if I'm loan worthy. They can send you a proof saying, yes, I ran my private loan worthiness procedure, which was approved by someone you trust, okay, who said, yep, it doesn't seem that racist to me. And the result was, you are approved. Okay? And that way, you can get the loan determination without, while knowing that it was really the right program, this right approved program, and without, without any of, without the lender having to reveal their program. Yeah. Does that make sense? That example? So the idea is like a snark. It's like this kind of like magical tireless like whistleblower and watchdog that will watch everything you do and scrutinize everything you do to make sure that you're behaving in accordance with some specified algorithm. Does that make sense? It's like what I like to think about is I like to think about Volkswagen. Does everyone? know about Volkswagen? Yes. Who knows about this thing like with their like emissions regulation? Yeah, like they had a thing in their car that said like, oh yeah, if you know some environmental factors are such that I think that I'm in the emissions inspection laboratory, then be very fuel efficient and don't produce a lot of emissions. But otherwise, yeah, do the other thing that like gives better performance and creates lots of emissions. Okay, so that's what they did. And that's really bad. So SNARKs have nothing to do with that, literally. But they sort of do metaphorically, right? Like, it wouldn't be with SNARKs, but you know, imagine if you have some regulation that you would like to enforce. SNARKs will kind of let you be this watchdog that's always watching and making sure that that regulation is enforced. Do you see what do people see where how I'm kind of painting this analogy? I mean, it's not a perfect analogy, but yeah? I'm just trying to give you a sense of what kind of applications you might want to build. Okay?
I'm curious about how much, so like the succinctness aspect, so it's going to prove this some kind of input data. Well, what is the maximum amount of bits that can be like verified by the SNARK? Like, whatever the statement is, it takes up some amount of bits of information.
The question was, what's the maximum size of the statement that can be proved by the SNARK?
Right.
It can be very large. So like your witness could be some extremely large value, gigabytes even.
But what is that a function of? Where is the limiting factor here? On the SNARK or on the machine?
It has, in practice, it really comes, it really like, at some point it becomes too inefficient to run on a single machine.
But that's not the actual
Theoretical?
right.
There's no theoretical limiting factor. There are only engineering limiting factors. Okay, cool. We good? We feel like we got a taste of that SNARK app juice, and we understand what the fruit looks like, so to speak. Yeah, Snapple. Very good. That's very good. I'm gonna steal that. Okay, that was Joey. Thank you, Joey. I'm sorry, I said your name. I don't know if you didn't want me to, but okay, great. So, cool, very cool. We end at 3:30, is that right? Yeah. So here's what we're going to do. At 2 o'clock, I'm now going to talk about SNARK constructions, okay, until 2 o'clock. At 2 o'clock, we'll do some exercises. I know we really cut into the exercise time, but I think what I just said was, who thinks what I just said was sort of useful? Oh, yes. So, and the exercises are, you know, it's text files, right? You can look at them. So, and there's comments. So I'm going to talk about SNARK constructions, then we'll do exercises, then we'll try a demo of the voting app. Okay, because that's, you know, it's just kind of fun, right? You'll be like the first, if we do that voting app thing, like this will be like the epicenter of like, you know, this will be like the first Snap. You'll be like the first Snap you know what I'm saying? Users, except for Zcash. But like, for Zcash. So the second ones. Which is kind of actually really exciting because I don't know if it's clear to everyone else, but I feel it's so clear that this technology is actually extremely useful and important if we want to build, you know, if we want to build computer programs which are sort of forced to behave in accordance with our norms and you know, it's the only way. It's kind of the only way. So, and you know, in 20 years, when like we're all like verifying 1 million SNARKs a day, you'll remember I verified some of the first useful SNARKs. Okay. I actually believe that. Okay. So, great. SNARK constructions. So here's what a SNARK construction is. You write your program. There's an arrow called a SNARK construction. which is some magic, some special cryptography juice. It's not magic. It's not even that complicated, but we can't explain it in an hour from nothing. But it's not magic. Anyone who says it's magic has something to sell you, or whatever. It's just some cryptography. It's not that complicated. Crypto, and at the end, you write this program and you run it through the construction, and that's what really gives you like these little proofs and so on, and the verifier and the prover. Okay, and so there's various constructions. They have various security and efficiency trade-offs, and we can talk about them. Okay, does it make sense? So let's talk about them. I have a little bit of a. Oh, what's up? Oh, should I turn off my notifications? Should I leak some sensitive information?
Not yet.
Okay, all right.
It might just be distracting.
I'll just kill it.
Yeah, thanks.
Great. So, constructions. Oops, sorry, Bobbin. Oh, I know. They're here. Which SNARK is right for me? You might ask your doctor. That is your PhD in cryptography. Okay. So, I put a lot of question marks in here because I didn't know. I made this the other day. All right. Here are the things that you care about when evaluating a SNARK construction. It's really simple. You want to know, so here's all the constructions. Here are some popular ones. Got Grot 16, that's kind of the OG, like the OG good one. Bo Gabson 18, that's like another version. Marlin, that's like a recent good one. Plonk, also a good one. Sonic, also a good one. Like more OG, like not as good performance-wise, but like also kind of good. Fractal, that's like a cutting edge thing from like 2 weeks ago, but also really good for other things. Okay, so those are names. Now, the first thing that you want to know is this setup. Remember we talked about this accursed trusted setup, right? That somehow you need to trust someone to generate these keys, or the alternative is you run like a big multi-party so-called computation where everyone gets out their computers, and then we, each of us like run some program to like contribute to the keys, and then at the end we all take hammers to our computers, and then so long as one of us was honest and really destroyed our computer, then everything is okay. Okay? That's the dreaded trusted setup. But the trusted setup, it can be, there's two gradations of how horrible it is. The way I like to think about this is, how many setups do you have to perform? 0, that's the best, obviously. 1, 1 is pretty good, right? If we only have to do that once and then we can all forget about it, that's pretty good. Or infinity. Those are your options. 0, 1, or infinity. So 0 means that's good, right? That's good. That means we can just go. Fractal gives you that. There are others that I didn't list. STARKs, for example, if you heard about STARKs, are also kind of SNARK that has no trusted setup. Okay? That's good. The second is 1, okay? 1 setup. 0, 1, infinity, remember? So we did 0, now let's talk about 1. Those, you usually call that a universal setup, because you just have to do it once, and then you can use it for whatever program you want. Okay? Does that make sense? Yeah, question.
So it's some sort of like hash that everyone knows that's published online. This is a swap hash, or like this is a private key that you need to set up.
Yeah, so the question was some kind of hash that's published online or something. Yeah, it's just some piece of data that like we all came together and generated, and like cool. Now we don't never need to do it again. Let's not talk about it. Yes.
To be clear though, when we say per program, we really, like for example, our election, that was the program. But the instance of doing another election over and over,
we don't need to redo the setup. Yes. So so that's universal. Like whatever snarky, all the things that we talked about today, we would only need to have done one setup, like period, and then everyone could go and do whatever applications they want. Now, the reality is, some of these, it's a little unclear. Like, you could kind of piece together from the data that exists like reasonable universal setups, but it's like someone has to redo another one. I think there's one going on, by the way, right now. I think it's with Aztec. So I think they're doing one right now. If you want to be one of those people, you know, and then 20 years from now, you can be like, I remember when we still had to do setups, like, and I participated. I like, you know, took my computer in an airplane and then like threw out the then like opened the airlock and like threw out the window to destroy it. Okay. And then the worst, so that's 0, that's 1. The worst is infinity. So infinity means you have to do a new setup for each program. So we wrote the selection one, setup. We wrote the pre-image one, new setup, blah, 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 blah. Okay? Yes?
But what invalidates, like, whatever the output of the prover is?
What invalidates the trusted setup? It's whatever.
Like, what forces you to redo the trusted setup?
It's just a fact about how the cryptography is implemented, that it somehow the setup key, the keys, the proving keys and the verification keys depend on the program.
So that's more a function of the cryptography used, not the actual, like, what I'm sending over. Like when we had the election example, it was like the election ID and other stuff.
Yes. And any of these, you know, we could use that same program that we wrote and implement it using any of these SNARK instructions, right? We could start with the same program, then we could say, oh yeah, let's build that using something that we need a setup for. Let's build that using Fractal, where we don't need a setup.
No, but I mean, in the thing we had the election ID, but now I add my favorite color to the payload of the hash. And this requires a new trusted setup?
So if you edited that snarky program, then you need to do a new setup. But you could make yeah. So the one where it said per program, that doesn't mean that every time we make a new proof with a different input, a different statement, a different public input, we don't need to do a setup then. You do a setup once for the program, then you can do it. You can make as many proofs with as many different public inputs as you want. Does it make sense?
Arbitrary inputs.
Yeah. Yes. Yeah.
How big is the setup?
How big is the string?
The setup.
How big is the actual proving key, or?
The setup.
What's the, sorry, how big is the setup? What do you mean? The proving key, or how much data?
Yeah.
So it depends on the program, but like, for example, I don't know, like let's look at like the pre-image thing. So this was a pretty simple program. The proving key is 200 kilobytes, and the verification key is 4 kilobytes. Pretty small, but it depends on the program. It's linear in the size of the program.
But this is not the setup, right? This is setup.
This is sort of the result of having performed the setup. The proving key and the verification key.
For example, the voting example, you have like a million people doing it. Then the key will be very hard.
It will be larger because it's a more complicated program.
Maybe gigabyte.
Probably not that big, but if you had a complicated enough program, then yes, it would be. Yes?
So you mentioned when generating the
Sorry, let me just say one thing. So the question was like, oh, would it be a gigabyte? How big would it be? That's only for the proving key, not for the verification. The verification key is still small. Yes?
You mentioned when generating these PK or VK files, there's some toxic waste that's generated in memory and then discarded before
Correct.
after you write the files out.
Yes.
Is it true that in these universal setup constructions that we need to trust that whoever created them doesn't have that toxic waste?
Yeah, so the question was like, oh, when I made these proving key and verification key files, there's some toxic waste that was like, you know, in the memory of my computer and then discarded and not saved to disk or anything. In the universal ones, do we need to trust that toxic waste was discarded? Yes. The universal ones also have this property that it creates so-called toxic waste. But what you can do is have a ceremony with many people, and so long as one of them destroys their share of the toxic waste, everything is OK. If one person does it, the whole thing is fine. Good question. OK? Yes, Joseph.
I guess part of just if you can give a flavor about the difference between SNARK and SNARKs, and why are people calling themselves transparent SNARKs rather than just SNARKs?
Transparent, SNARK, yeah. So transparent snark means snark with no setup. It's a bit of unfortunateness in the nomenclature. Stark really ought to mean a snark with no setup, okay? But they wrote this paper about this particular snark with no setup, and they said this particular protocol, this particular construction of this particular snark with no setup, it's called Stark. But really, it should be a more generic term. And that one should be renamed to like Stark_0 or something. Huh?
Mark 1, like Iron Man.
Yeah, Stark Mark 1. Okay, sure. Or Tony. Maybe Tony. Okay. All right. With me so far? All right. So that's somehow kind of like from a practical perspective the most important thing. It's getting better. Like some of these constructions didn't exist like literally a month ago. Okay. So like in the last year we've seen a lot of development. It used to be that we just had these per program setup SNARKs, plus this one kind of practical protocol for zero setup STARKs, but it had some severe limitations. In the last year, we have very convenient to use universal SNARKs, one-time setup, and also quite a convenient zero setup SNARK, which is fractal, quite convenient. Because it's compatible with sort of existing tooling. That's why it's convenient. The other thing, STARKs, it's sort of extremely incompatible, and Bobbin will talk about it a little bit. This thing is oh, you had a question? No. This thing is sort of something that doesn't get talked about too much, but okay, so SNARKs, like there's this question, is a SNARK malleable? Who has some intuitive sense of what malleable means? It means that it can be changed. It means you can stick your fingers into it, and like clay, and you can smush it around. Okay? But in the context of SNARKs, what it means is you can take it, and you can take a good proof, and you can stick your fingers into it, and screw up the bytes, and make a new proof for a new statement that you shouldn't be able to prove. Okay? If people it's like with digital signatures. If I can take your signature and I can reuse it for another message, that would be really bad, right? It's like that. So by default, some SNARKs actually are malleable. Like Grot16, famous SNARK, is malleable. It's kind of bad, but it can be fixed. This Bogabzin 18 is basically a little patch on Grot16 which makes it non-malleable, makes it impossible to smush it around. Usually you want it to be non-malleable. Just if you don't want to think about it, just like pick a non-malleable SNARK. It's a very small performance overhead. It's very small. These ones, I think they're non-malleable, but I wasn't totally sure, so I just put question mark, but I'm pretty sure. Okay, so that's that. The next important metrics are how big are the proofs, how long do they take to make, and how long do they take to check, right? Make sense? So in terms of the proof size, these constructions, if the ones that have some setup, this is why you see the setup is you really want to taste that setup juice. Because you get really small proofs. So with Grot16, which has this per program per setup, you get like 100 byte proof. On the other hand, if you want to use like a universal SNARK, it's going to be like 1 to 2 kilobytes or maybe even a little bigger. And then, ooh, you don't even want to see this. If you want to use the no setup SNARK, it's going to be like 80 to like hundreds of kilobytes. Ugh. But that's from last month, so hopefully we'll get better soon. But you really see why you might be like, oh yeah, why not just like everyone use Fractal, right? This is why, because the proofs are really quite large compared to like 100 bytes. Think about that. That's nothing, right? Okay, so that's prover time and verifier time are also things that you might care about. But they're all not so bad. That's it. Okay. That's about SNARK constructions. I only went 4 minutes over, so that's very good. Pranay, yes? Can you give some heuristics or about why this trade-off exists between this, like the proof size and the setup time? Yeah, that's a really good question. So I guess is this working? Test? Okay. So I guess what I'd say about that is I can't really give like a very good intuitive. I can try and work backwards from like the actual fact to like an intuitive explanation of that. So like the actual fact is the way that we know how to do okay, it's a snark. There always has to be some cryptography in there at some point. You can prove that, or else you can't make a snark. There has to be some cryptography. I'm not going to explain that claim, but for some definition of what I'm about to say, if it's a snark, it needs to use cryptography somehow. You have two options. Well, you have more than two options, but like, okay, anyway. What you can actually instantiate, what you can actually use as your cryptographic building block is maybe either like a hash function or like some elliptic curve stuff, okay? So the no setup ones, they use hash functions, and everything ends up sort of like all the parts of the proof end up being like these giant paths in Merkle trees, which are quite large, right? If I give you a whole path in a Merkle tree and then I have to do it many times or whatever. Whereas everything is like on this little elliptic curve, and I can just like, it's constant size, and I can sort of play inside of this constant size thing. I don't know. I guess it's because like here you have like a hard object with a lot of structure, which is an elliptic curve, and here you have a hard object with no structure, which is a hash function. And when you have no structure, like you just, I don't know, you have to do like, you have to do simple things, and the only simple thing is like I don't know, Merkle trees or something. So you just don't have that much flexibility, and like, yeah, I'm not sure what to say more than that. Yeah. Yes.
Is the fact that Groth16 is malleable, is that like breaking for systems that use Groth16 as their SNARK implementation?
It could be. So let me give you an example. Like in Zcash, okay, Zcash, there was a larger issue in the SNARK implementation that I won't touch on. But in Zcash, they use Groth16, but they also really need non-malleability of some kind. So they have this kind of little patch on top of Groth16 where like, it's a little complicated to describe, but like you have to like provide not only the SNARK, but like a signature on the SNARK, which is like a little patch. But otherwise it would be broken if they got rid of this little patch. Other questions? How is the non-malleability compared to the soundness? Non-malleability is okay, so like if you want to look in the papers, crypto papers, they call it simulation extractability, is this kind of very strong non-malleability. And it's a kind of soundness. So there are several, this is a little bit technical, but there are several kinds of soundness. One you might call knowledge soundness. All of the SNARK constructions are knowledge sound. That's what the K really stands for, knowledge sound, okay, sort of. So they're all that. Then there's also the stronger soundness property, which is simulation extractability, and that's like non-malleability. If you read, if it's in this this documentation, if you want to peruse it later. Okay, cool. All right. So now, great. It's 2:08. Oh, these didn't stop. Okay. Let me just kill Discord. Oh, you know what? I have a command for doing that. Okay. So now we're going to do exercises a little bit, just to give people a little bit, we talked about sticking your fingers into the proofs. Now you'll stick your fingers into the programs that make the proofs. Again, let's recall, everything is in this, so in this SFBW workshop repo, if you just navigate over to problems, oops, and I would recommend taking a look at, say, first this EX Merkle list. Okay. It stands for either exercise or example, depending on, I don't know. Okay, so this is going to be sort of, you saw like in the standard library, like we have this like Merkle proof check thing, right? This is sort of you're implementing that. Non-Merkle proof, but it will be like a Merkle list, like a hash chain. Instead of like the tree, it will be just like a chain of hashes, and you'll check sort of membership in that list. Does that kind of make sense? You'll see in the example. And if you want to, so if people git pull in that repo, I push that like reason example file that I had before. So you can take a look at like how the syntax looks, like how do you loop over an array, and so on. Sound good? It's in reason_example, and then this exercise is in ex Merkle tree in problems. So maybe we would take 20 minutes and do that, and make friends with your neighbor, and so on. Yes, Edgar.
Sorry, coming back to the SNARK construction.
Oh, sure, yes.
That the proof part, providing the proof, that's computationally intensive. So is it beyond the reach of the latest iPhone, or still at the moment? Like, how long would it take the latest iPhone to create a Merkle tree? Is it like 3-4 minutes?
No, it's like no time.
It can still,
Like a second? I don't know.
not the verification, I mean making the proof.
I know. Yeah. So like the reason that is, let me just say, in addition to all these new SNARK constructions and so on, because of this particular interest in SNARKs and the particular interest, in this particular model of computation where the only thing you care about is multiplication and so on, there has been some development of cryptographic primitives which are extremely efficient in this model of computation. So like there are now new hash functions which are super efficient inside of SNARKs, which is why it's like, like a second or even less actually.
So what kind of business logic right now is a little bit too beyond the reach of the computation?
Most business logic is not a big deal actually at all. So like you'll see. I think try and do the example and we'll talk. We'll come together and we'll have more time for Q&A after. Is that cool? Okay. Oh, the question, by the way, was about how long does it take for an iPhone to generate a Merkle tree proof for anyone watching the video, and the answer is like a second, or maybe less. Probably less. Thanks, less. Okay, please, everyone talk, it's casual. Into the bytes, so to speak. I'll now just kind of go over the solution. I know it's like new syntax and stuff, right? So that's kind of the real hard part, right? Everyone people kind of understood the idea, right? And it's like with everything with a new programming language, you just have to like, at some point you just learn the syntax and then your fingers know it forever. Let's just have a look at the solution. So, all right, so it's quite, it's just some syntax. So we have some accumulated hash value. We initialize it to that the value that we want to prove is in the list, x, and we loop over our path, and we hash in, for each I, the ith entry of the path with the accumulated value, and we set the accumulated value to be that, yeah? And then we just say, oh yeah, that should be equal to the supposed root. Make sense? Okay. That's about it. Yeah. Someone question? Yes. So, in functional programming land, mutation is extremely explicit. So, like, variables are not mutable. They are immutable bindings, immutable names given to values. And if you want to have a mutable thing, you need to explicitly say, like, this is a reference, which you initialize to some value. And then when if you want to extract the value out to dereference it, it's this caret syntax. And then colon equals is how you like set the value. Does that make sense?
Is it possible to just call main recursively with the rest of the list, the rest of the array?
Yes. So I wouldn't do, so main has to, yes, main just takes the witness, but yeah, you could do that. Yeah, you could just do that actually. You could just say like, so you could do this recursively and be like, oh, let main, this is maybe too, probably for most people it won't be helpful, so I won't do it up here because most people are used to programming imperatively, so we can just live with that. But yes, exactly. Yes.
Question. So in the example, I see that you initialize path. You use consecutive values from 0 to 31. Does it have any
No, this has no meaning. These values are meaningless. They could be anything. Yeah. Okay. Very cool. So I think now this is just to give you guys a sense of what's possible. You know, we don't have time to do every exercise. It's not the end of the world. So okay, so there's two directions we could go in. I want to take a little straw poll. Who wants to see like how like Merkle-proof checking would actually be implemented? Like how do you do conditionals basically? Yes, good question. Sorry, I should list both alternatives. That's one thing you could do. Another thing you could do is just use the built-in Merkle membership proof checking function to like basically prove something about a database of people. Say like, I know a person in this Merkle tree whose favorite color is this given public input and whose age is greater than 30. So this is like a step closer to our voting application. That's more interesting, right? Oh, who says the first thing, which is sort of like kind of more sort of low, like algorithmics? And who says the second thing, which is like this like kind of application where we prove that we know this person is over 30? Well, the beautiful thing is actually we don't have to choose. I just realized that we're not doing these together. So pick whichever one is your favorite. If you're interested more in this application one, check out this Merkle tree with data exercise. And don't forget that you should run, Merkle tree with data. Don't forget that you should run npm install and npm run build to get autocomplete and nice stuff working. And if you're interested in sort of the algorithmics of how you would implement like checking a Merkle proof, check out ex Merkle tree. And if you get stuck, you can look at the solution, and no one is judging you. And then we'll come back in 20 minutes on the dot. Okay, I am very sorry. It sounds like everyone's having excellent conversations and hacking and so on. In the interest of time, we need to bring it back. It has been so real. I really mean that. I really appreciate everyone's. It's been a lot of good energy today. I think, at least from my perspective. I don't know if other people feel that way too. So thank you for coming with open minds. All right. So in the interest of time, I'm not going to go through the solution. It's in the text file. You can check it. You can check it out. Let me just say one other thing that I wanted to just to bring it back to the SNARK construction. Well, let me just give you a few takeaways that I wanted to give today. Okay. There's like basically 3 things. Okay. The first is there are very many cool applications that are waiting to be born, and it's like what I said about like in 20 years, like we'll look back and be like, SNARKs, wow, like are really actually extremely important and enable all these amazing kinds of applications that empower users to have accountability over the software that they're interacting with. I really believe that. I really believe that will happen. At the end of the day. On the other hand, it's a political question, and it will only happen if there are programmers who want to program those things and pressure their companies into making those things happen and so on. So it's a political question, but anyway, politics and technology, they require each other. That's the one thing. The second thing, SNARK construction. This is changing gears a lot from what I just said, but SNARK constructions. There are a lot, but you don't need to know that much about them somehow. What I showed in that table is like enough from an application developer's point of view about which they want to use. That's the second thing. The third thing, even though I just said you don't need to know about them, if you want to know about them, they're also not that complicated, but there aren't that many people who understand them well in terms which are not very technical or complicated. So I don't know how to square that circle, but like sometimes, sometimes one thinks in one's mind, oh, this is sort of an insurmountable, understanding this is sort of insurmountable, and only some kind of magic genius could possibly understand this, and so on. But I'm just trying to tell you, I'm just trying to like, give you the impression that actually that's not true, and anyone can understand it. It's really not that complicated. That's all I want to convey. Does that make sense? Probably there have been things in one's life that seemed insurmountably complicated, and then one understood them. It's the same. It's not magic. Everything is this way. So that's the only other thing that I want to say. And just one more kind of shout out. If you go to this codeprotocol.com/doc/snarks, there's all kinds of nice information about things you might not want to know about snarks. Again, do I want Stratera or like snark? That's a medication. I'm joking, but which snark you want. And the other thing is, if you go here to our chat, we can, even though the workshop will be over, we can still keep talking forever. And with that, I will hand it over to my colleague Nathan, who will be leading us through the fun voting demo, and we'll all vote on whether ketchup is good or not, and we'll finally know the truth. Thank you.
All right, so we have a voting demo that's deployed in Amazon. So we'd like to have everybody try and connect to it as a voter and see if we can actually do elections. So in your Docker container, you'll want to set this up in your Docker container because that's where your working environment is for actually building all this. All I want you to do is just go ahead and clone the repo. This is the command to clone it. And there will be a series of commands here you run in order to set up the repo once you clone it. And then what you'll want to do is you'll want to set up a voter JSON file, which will basically describe who you are as a voter and what your age is and first name and things like that, attributes that you might be interested in constraining for who can vote in elections. So you'll just copy some sample file over to a new voter file and then edit it.
So I'm going to be doing it up here if people want to like see what I'm doing.
We have to run this inside a Docker?
Yeah.
Wherever you have your the build working and so on.
Yep.
Okay, so I just cloned it, and then I ran npm install. Now what do I do, Nathan?
Now npm run build. And then you should copy a sample voter file over to like me.json or something.
Source?
Oh, sorry. Let me push up a sample voter file. I had ignored those. I forgot about that. It'll just take a second. OK, sorry about that. So now if you git pull that repo, there will be a sample voter file, sample.json. And so you can see this file basically, remove the private key. You'll want unique private keys. If you remove it, it'll just regenerate one for you. So make sure you do that. And you'll basically just go through here and edit your attributes to whatever you want.
So is this sample.json?
Yeah. Yeah, just delete the private key value pair.
It's a good movie. Hello World, great movie.
I got error when I'm doing npm run build.
Did you do it in the Docker container? No?
I should run it inside Docker.
Yeah, you should check out the repo and wherever your builds are actually working. Yeah, if you manage to get through all this and you have your voter file locally and you're ready to go, you can go ahead and run this command, replacing this argument here with whatever your voter file that you made is called.
Space.
Yeah, this is weird syntax. There's like a dash space here.
Yeah, I did it up here if you want to copy what I wrote.
Yeah, there we go.
And it worked. I registered successfully, and I'm waiting for registration to close.
So once we get enough people connected, I can close registration and we can actually make elections.
Does run voter generate a key pair? Or
The key pair was generated on the server by Nathan.
Oh, are you talking about the proving verification key pair?
No, sorry. So
For the private key.
in me.json. So I took the sample.json
Yeah.
and deleted the key pair.
Yeah,
the key there.
when it loads that file, it'll generate a new private key for you and save it back in that file.
Sorry, can you say that again?
Yeah, when you load the JSON file for the voter, it'll generate a new private key for you, and it just saves it back in that file for you.
Oh, I see. When I run step 7.
Yeah, when you run step 7, it'll generate it for you. Yeah, sorry. So we have 4 people connected. That's exciting.
That's cool.
I'm kind of worried this isn't going to scale that well.
We'll see.
We'll see if it works in this network.
And it's not under sample voters anymore.
Are you doing it in your Docker? Oh, yeah.
Huh? Should I write this video?
Yeah.
No, just fix it.
What's wrong?
Just do cp-sample.json.
Oh, yeah, sorry, because, yeah, that was the one I had uploaded.
I did run that command and it just like fails at the last step.
Which one?
You know, yeah, there. Do you want me to rerun it?
Holy.
Do you want me to rerun?
That's so weird. Undefined line 14. You did an npm install, right?
Yeah.
I don't
Yeah, I did.
understand
I
why
can
that's
do an
happening.
npm
Yeah,
install again. But I didn't run npm install after you pushed.
You can just.
you shouldn't need to.
Oh wait, did that?
I don't know.
I'm sure I
Go after
did.
you make your.
Yeah, I'm sorry. I
That's okay.
don't understand what that error is.
Oh, okay, maybe.
It's saying a syntax error on a JSON file. Oh, your voter JSON is not correct.
Me.json?
Yeah, me.json has invalid syntax. That's what it's complaining about.
Oh, whoops, the comma.
Yep.
Okay.
9 people are. You wanted us to delete the private key, right?
Yeah, delete the private key. Yeah.
Okay, but yeah, we always got delete trailing.
Yeah, sorry. I should have given more explicit instructions there. So hopefully now you can connect with that.
Change your. Delete your private key. Just register. Yeah.
Anybody need help?
I think I'm in.
You're in? Nice.
Can you tell though? Because it's like a zk-SNARK, right?
Well, I could look at your commitment, but I wouldn't know your information.
Okay.
Although I don't have a command on the console right now to look at your commitment. But I can just see how many people there are right now.
Right. I'm pretty sure I'm in there. It says like just registered and waiting for the
Yeah.
Change the private key.
Do you have to do what?
To change the private key. Edit.
Just remove it.
Remove.
Yeah, completely remove it.
Okay.
Yeah, I shouldn't have checked it with that.
And also the comma.
Yeah, and also the comma, yeah. So how many do you have? 14. This is exciting. I have attribute constraints in too, by the way.
Oh,
You can like, when you create an election, you can say like, oh, only people who are 24. How are we doing in time?
We have 25 minutes.
Okay.
We will close registration in 5 minutes.
Make sure you register.
Otherwise, yeah. So the voters.
Don't worry about keeping your process open because once you register, you can reconnect. So if your process dies for some reason, you can just reconnect.
Do you have to use the same JSON when you reconnect, or?
Yeah. Because that JSON tells it all the information about it.
Should
Yeah.
I just like DDoS you guys? Like just start like.
Please don't.
For a loop, like.
I definitely did not build this to be preventative against DDoS. Please don't do that.
I won't, don't worry. I'll slow Loris, you guys.
Oh, no, no, no. That's actually worse because it's a WebSocket server. That's more dangerous than the DDoS.
Nathan, it doesn't says like connected, but not.
It should say connected a few times before it does it successfully.
And then his one is hasn't even printed connected yet.
It's probably the internet's struggling.
Oh, okay.
Wait, really?
We're at 16. These are WebSocket connections, so they won't scale forever. But I would think that we can fit more than 16, right?
I don't know.
How many people here are having problems connecting? Too busy.
The internet.
It's the internet, yeah.
Something happened with internet.
Well, whenever you connect, you download like 2 megabytes of keys, so it's probably just killing the internet, everybody connecting at once. Oh, 19. That's pretty good.
All right, should we just call it?
Let's give one more.
All right.
I don't know.
We said 3 minutes. Yeah, I'm gonna go bathroom.
Yep, feel free.
Where is it?
It's just through there. You'll see it on your right. We're just going to give a couple more minutes for people to get registered. If you're having issues, just raise your hand.
Yeah, you might be. That might be like an aesthetic that you might buy with. Okay. Wall Street bets? Yeah, it's just people doing shit on Robin Hood. Like someone will buy something.
Were you able to connect?
It's connected. I mean, it does that.
Oh, yeah. Try restarting it one more time.
Oh yeah, I did restart it, and then okay, I still have my connection there. Okay. So.
Yeah, we're just destroying the internet right now.
Okay. Any thoughts on GAD? Because of like all like the.
Yeah, he's the average.
Want to buy 6 flags?
Shilling like the worst things.
That's so funny. Something.
Definitely people who should not be buying options.
Generation Z. Dude, I'm probably gonna get AirPods. I just have like the wired ones right now.
Oh yeah.
I literally got them like less than a month ago and they're already free. Like the wired ones.
It sucks. Yeah.
Such an L.
Wait, is it like the default one?
Yeah, the ones that come with
Like
like
a new iPhone.
with the lightning port.
Oh yeah, yeah. No, those are. Yeah. I'm just worried to get
Okay.
AirPods 'cause
I think we're going to close registration now. So hopefully you were able to connect. Let's see if this works. Well. It's not working on Izzy's laptop, but hopefully some of you are seeing a voter prompt now. Is anybody seeing a voter prompt?
I got a
Okay.
failed error.
Oh, you got an error. Okay.
Already registered. It appears to have tried to.
Try and connect again.
Okay.
You just reconnected during registration.
Okay.
Okay, it looks like Izzy's is not working, but for people who are connected, you should now be able to create and see elections. So if you type in create and then quotes some name of an election, like my favorite color is blue, it should actually create an election, hopefully.
How do I?
Yours finally started working.
I restarted it.
Oh, okay.
Create what?
Like a string, just like double quotes, whatever you want. And then.
Someone already voted on it.
Oh, okay.
Wait, should it be a question?
Yeah, it can
It's
be a
string.
question. So if you hit list, type in list, Izzy, you can see all these over here on the left-hand side. These are the commitments to the elections. This is basically the IDs for the elections. If it's green, that means you're able to vote on it. So you can also express constraints on who's allowed to vote on elections. And so if you select one of those and you copy the ID for one of the elections, you can type in vote and then the election ID and then Y or N.
Ketchup is good. I encourage you this October to vote yes on ketchup is good.
And now that you've done that, Izzy, if you type tally and then the name of that ID of the election again, now it will tell you that 3 people voted yes and 1 voted no. And let's make a little more interesting election. Can you create an election with a constraint this time? Like, what was the favorite color you put down?
Blue.
Okay, put down an election for people
How do I do that?
who, so give it an election title like, I don't know, I'm wearing blue right now. I don't know. And then say that favorite underscore color equals blue.
Like that?
No quotes on that one. Sorry, I didn't implement the quotes there. So now if you list them, it'll show for you right here that you're wearing blue right now, and that's OK for you because you have favorite color blue. If you make another election with favorite color equals green, it'll be red instead. Is this off?
It was, there you go. Wow.
So people who do not have the favorite color blue should be able to type list and see this election, but it should be red. Huh?
What if it's blue but it's capitalized?
Well, right now it wouldn't work. Under a better system, you'd probably
But you
like.
could do it.
You could, yeah. How do you vote?
So you do vote, and then you put the ID of the election. So like, let's say, okay, I don't know. Some of these are a little controversial. Inception movie is awesome. I vote, and then I put the ID of that election. It's this big ass hash. And then I'm like, no. It's Y or N. So I'm like, nope, I don't like it. Then you can list, or no, then I say tally, is that right?
Yeah, tally and the ID will show you the count. Yeah, votes are always yes or no. But you could create a system where votes have like multiple choices, and you could list the choices for votes.
This is really cool, Nathan. In the future, you'll be telling your children that ketchup is good, and that's what you found out using SNARKs.
Eat this money.
Hey, someone still has a flash drive or a dongle from earlier. Can you just raise your hand?
Ben Lambo? Yes. Can we all just make like things to vote on? Yeah.
Yeah, anybody can make an election.
And then a proposition, and then optionally parameters for like you're like restricting it so that you can vote on it. How do you do the constraints again?
Here, let me turn the mics
Oh,
off.
I see. Okay, cool.
Yeah, you can give multiple constraints as well. So if you want to put a constraint on an election, you can provide a key value pair separated by equal for any of the attributes that were in that voter JSON.
What happens if I try to vote on that one?
Hopefully you can.
Oh yeah, so it's in red, and I'll be like tally. Vote. No. Cool.
That's cool.
Nice. Yeah, that's awesome. Cool.
So this could be like a whole social media.
Yeah, like a whole thing.
Is there anything fun we can do?
So what
I guess about it, just let people play with it.
points of failure in such a system? Is it that like the central authority can censor?
Yes. But it could be a blockchain.
Yes.
Yeah.
Wow. Okay.
And this is not blue shippers. Like there's like you can bribe because you can prove your vote.
Turns out it's good. This ketchup is good.
Sorry, what do you mean by the bribing thing?
Oh, like, so you can prove what you voted for. Like, you can conclusively present to someone, for example, if like this is protocol being run on chain.
So you mean like proving that I was the person I was a person and I voted yes on this?
Yes.
Yeah, you'd have to make another snark for that though.
Yeah.
Because in this snark, we're hiding the membership proof in the witness.
Yeah.
So when you look at that snark proof in the inputs, there will be no input that says that you're actually that person.
You could reveal your private key also.
Oh, you could do that. But then you'd reveal your private key.
Make a burner account.
There would be, you could implement with signatures. You could then, give somebody a public key and they could check a signature or something like that. Yeah, I mean, yeah, that's pretty much it. I want to go through and see what all the tallies were. Yeah. I don't have a script to tally all of them. I should have made that. It was a mistake.
Sorry.
Yeah.
Can I just close it?
Sure. Yeah, close it up.
Okay. Thanks, everyone. I hope that was fun. Was that fun? Election, public election. Who learned something today? And it's like, yeah, that was actually a pretty good use of time. At least some people. That's great. Okay, so thank you, everyone, so much for coming. It might sound like I'm going to say it's over, but it's not over. Actually, the fun is just beginning.
Hello, everyone. Very excited to be here, and thank you, Easy and team, for having me here. So today, I will be talking about AirScript, and it's a language that you can use to define computations for SNARKs. And just a show of hands, how many people have heard about SNARKs before today? OK, decent amount. So the goal of AirScript is very similar to SNARK in that the idea is that you should be able to write defined computations, and you don't really need to understand a lot about how SNARKs work behind the scenes, so you would be able to write it and kind of compile it and run it. That's kind of the overarching goal. And AirScript is very different from how, it's a very different mental model from how you would think about writing programs in general, but also very different from how you would write programs with snarky or some other languages. And the first thing I want to do is kind of give you a quick overview of how you can think about different types of computations, specifically for zero-knowledge proofs. So we can roughly think about computations as in two different categories. They can be expressed as circuit computations or machine computations. And the representations for those computations are different. So circuit computations are expressed as or described as arithmetic circuits. And this is where you would have kind of a circuit describing the computation completely. And machine computations, they're usually using transition functions, where you would define a transition function that kind of describes how a computation state changes from one step to another. And then this transition function gets applied to many different steps. Once we have a representation of a computation, the other thing that we need to do is kind of translate it into kind of a set of polynomials, and that's the arithmetization. And here we have a couple of options, but the two primary ones are one-constraint satisfiability systems and AIR, or arithmetic intermediate representation. And because writing constraints by hand is very difficult, we have different languages kind of on a high level that allow you to write simpler code and then compile it to those constraint systems. And so for R1CS constraints, you have snarky, circum, zk-SNARKs, and like a few others. For machine computations, you actually have at this point, AirScript is probably one of the, if not the only one, but like one of the ones that exist out there. I'm not really aware of other ones that allow you to write things on the high level. And there are reasons for that, and I'll get into that in a second. Kind of benefits of the different approaches is that there is, for R1CS constraints, that's fairly established procedure of how you would reduce a general computation to R1CS constraints. And the other big selling point is that they're fairly easily composable. So you can define constraints in for one kind of computation and compose it into another computation. This is not necessarily the case for air constraints, or at least it's much, much harder to do that. So you defining kind of computations that don't have those repeated structures is very inefficient. And also, the composition is much more difficult. Actually, AirScript at this point doesn't have the ability to do composition, and that's something I'm working on. But the advantages of machine computations is that because they have this very succinct representation that can be applied to millions of steps, so to say, they're very fast. The prover time for them is faster, and verification could be faster as well. Although this is changing dramatically. This is a very dynamic field, and things are moving very quickly. But at this point in time, as far as I know, kind of the prover time for, let's say, a machine computation is probably an order of magnitude, or could be an order of magnitude faster than for kind of circuit-based computations. And now, what are they suitable for is, R1CS constraints can be really suitable for all computations, and you have to do some preprocessing, but that's not really that important. Machine computations, they're really good for describing some very specific computations that have those repeated loops and repeated structures. All right, so today I'm talking about AirScript, and AirScript is specifically for defining air constraints for SNARKs. And when I say SNARKs, I mean, like we had this mini discussion earlier, I mean the original SNARK kind of paper that described them, not a kind of a more generic set of SNARKs that are transparent. So for those, as I described, so let's go quickly through basic SNARK overview. How do we think about SNARKs? As I said, so let's say we have some inputs and we have a transition function. And as I mentioned, you apply this transition function over and over to a set of inputs, and you get something that is called an execution trace. And this execution trace is basically your table that you can think about a column as a register, and then every row is kind of how the execution of a program changes, or state of the program changes from one row, kind of from one step to another. Once you have the execution trace, the next thing you do is you apply transition constraints to it. And you get the constraint evaluations. And those really tell you if the transition between two different steps was performed correctly. And in this case, for example, you can apply them to two consecutive states. And if the result of each constraint evaluated for those two consecutive states is 0, then you know that your computation was conducted correctly. And then there are a few other steps that are not really important for the purpose of this kind of discussion. You kind of compose those constraints. You run the Fry protocol to prove that that the resulting polynomial of a flow degree. But really what I want to focus today on, and what AirScript really kind of cares about, is these first two steps. It's defining the transition function and transition constraints. And specifically, if we think about AirScript, kind of what are the goals for the language? It's first is to define the logic of how you generate that trace table, like how do you apply transition function to some inputs to generate a trace table. And the second one is defining logic, how to generate constraint evaluations when you apply them to, right now you can only apply to two consecutive steps within a computation, but in general you could think about a system where you have, you skip over some rows and you can check rows in a trace table that are more than one step apart. And then the last one is kind of how do you interpret the inputs that are given to the script, and how do you kind of put them into the execution trace? How do you start with those inputs? So what I want to do is kind of give a very simple computation, a very basic one, and show how AirScript for that computation looks like. So this is a MIMC computation. It's, for those who haven't seen it, it's very trivial. You basically have a single register, and in that single register, you take the current value, you cube it, and then you add some constant to it, and then you get your next state. So you kind of, every step, cubing the previous state and adding some constant. And the constant is not just constant necessarily, like it's a global constant, but it changes from step to step. So it changes based on the step. It could loop around, but it's not just a single number. So here is how AirScript would look like for the specific computation. And I'll go through this step by step. So the first thing we do is we kind of define what our SNARK is going to be, and we'll define what field we're going to work over. We talked about fields, so this is kind of a definition of very similar that we kind of discussed in the beginning of the day. You say which arithmetic field all your computation is going to happen in. So the next thing that we do is we define what is called a read-only register. These are registers that are not really affected by transition functions, and we're going to use that to represent our constant, that k term that I showed in the previous slide that showed kind of that we were adding to the squaring of cubing of the current state. And in this case, what we're saying our read-only register is going to be called k0, and what we're going to do is we're just going to repeat the sequence of 4 values all over again. So from every 4 steps, we're going to repeat the sequence of values. The next thing that we do is we define a transition function. So a transition function in this case is very simple, and let me kind of talk through this. First, we specify that we only have a single register in our trace. Second, we specify that for whatever input that we're going to provide, an input is going to be a single value in this case, but we could provide a list of those single values. But for each one of those values, we're going to initialize the trace, just moving this value into the kind of first slot in the execution trace. And then we're going to apply, in this case, only 64 steps. I could have made it much longer computation, but in this case, it's going to run from 1 to 63, including the initialization step. That's going to be 64 steps. And so within each of the steps, if you can see my mouse, within each of the steps, what we're going to do is just going to take the value. R0 refers to our current register, so the value in the execution trace at the current step. So we're going to take the value at the current step, cube it, and we're going to add the value of K0 that we defined previously here. Sorry, here. So, and that's how our computation is going to go. So every step beyond the step 0, we're going to repeat this formula, and it's going to generate our execution trace. So the next thing that we need to do beyond the execution trace is we need to specify the constraints. And in this case, the constraints are super simple. All we need to do is to verify that the current step, if we apply the transition function to the current step, it's going to equal to the next step. And in this case, again, the R refers to our current step, and N refers to, $N refers to the next step in the computation. So what we're saying, if we're going to take the current step, the value of the current step, apply a transition function to it, it should be equal to the next step. And for those who kind of know how constraints work, all this does is just flips it around. It says N, the values in the registers N minus the transition of R. So you'll get 0 if the computation is correct. Let me show a quick example of how this is going to look like. So basically, let's say we start. Oh, go ahead.
Quick question about the syntax. Why is there using one read-only register, transition one register? What's that?
Which one?
So all of these 3 blocks always have a number of 1.
Yep.
What's the meaning of that?
Repeat the question for the video.
So basically, the question is, why do I have everywhere specifying one register? And what's the meaning of the number 1 there? So the number 1 in different places means different things. So here, when I say one read-only register, meaning I will only have one column, one kind of set of round constants. Here, when I say 1, it will mean that I have one trace register. I could have more than one, and then I can refer to them by their index number. So R0 in this case is referring to that single register, but I could say R1 if I had 2 registers, for example. And I could have a register bank that is as long as I need to be. I mean, if it gets too big, it's going to be very expensive to compute, but you can imagine having 8 registers, 20 registers, and so forth. Does it make sense? Does it answer the question?
Yes, but maybe follow-up question?
Yeah.
Maybe super follow-up question? Why not name the registers? Why number them? That's cumbersome to work with.
You could do it. It's
register, 1, you clear register 2, and then it automatically infers there's 2 registers, and then
yeah. So the question was, why not name the registers? Why don't give them kind of actual name that you can use in programming? And there isn't really necessarily a reason to do that. It's simpler for the compiler to do that, but it's kind of first step. So there is no reason why I couldn't say it's going to be foo, bar, and so forth and so on. There are some. So I'll maybe get into it a bit later. OK, so. And the one with constraints as well, you define the number of constraints in there. So your number of constraints could be different from the number of registers. So you can specify 5 constraints or 3 constraints when based on 1 or 2 registers or whatever. All right, so just to run through the example of how the execution trace would be generated using this transition function. So first, let's start with our K0. You can see the values here just repeating. So we repeat 4 values, and then for the next set of steps, we repeat another 4 values and so forth. So it's kind of repeating in a cycle. Let's say we start with the value 3. And this would be, for example, in our I0 register, we would pass the 3 as a starting value. And then kind of the computation would kick off from there. But once we have that set up, transition function starts to apply. So first thing we do is, let's say we cube the number 3, and then add 42 to it, and we get 69. And then the next step is we kind of cube 69, add 43 to it, and that kind of, it goes until the very end like that. So any questions so far? How am I doing on time? Is there?
It's only 3:38 and you have until 4. Oh.
Okay. Well, in that case, so what I want to do is kind of show maybe a slightly more complicated example. So this is a Poseidon hash function. This is now using more than one register. This is now this is how you would apply different logic at different steps as well. So in this case, we have 3 registers and we have 2 input values. And you can think about this computation specifically as, let's say I have 2 values and I want to compute a hash of kind of combining those 2 values together. Poseidon hash functions work such a way that you actually need another register to do that, so 2 registers would not be enough. But so here we define 3 registers and 2 inputs. And the first step, the way we initialize our trace, is that we copy the 2 inputs into the first 2 registers, and then the last register is going to be initialized to 0. And this is kind of our, if you think about how I should execution trace, this would be registered across the top, the first row in a trace table. And then here the transition logic is slightly more complicated. So for those who don't know how Poseidon hash function works, it has, let's say it has 64 steps. And the first 4 steps will apply some logic, then we'll, for 55 steps, we'll apply some other logic, and then for the last 4 steps, we'll apply the same exact logic as we did in the first 4 steps. So this is kind of what this describes here. So here we have, for the last 4 steps, we will apply this formula, and this kind of block will resolve. MDS in this case is a named constant. In the current iteration of AirScript, you can't name registers, but you can have named constants. And here we perform this kind of symbol signifies a matrix multiplication. So you kind of multiply the result of this expression and do kind of like matrix multiplication with the MDS matrix. And this is kind of the constant matrix that is used in the transition function. And then for other steps, you kind of have a different different logic, because there you don't need to deal with the entire state. You only need to kind of apply some logic to the last register. And one of the interesting things here to show off is that we can actually have variables in AirScript. So you can define a variable and you can assign some expression to it. So if you have common sub-expressions, for example, you don't have to repeat them in your constraints all the time. You can assign them to a variable and then use this variable in the subsequent statements. And here what we do, take register R2, add the value from the read-only register K2, raise it to the power of 5, and then we build our output state by kind of combining. This is kind of mix of JavaScript syntax with some Rust syntax here, but basically we take the first 2 registers from our state bank, we take the first 2 registers from our constant bank, we add them together, and then we kind of spread the values and build a single vector of 3 values from these 2 and the V2 variable that we computed here. And then we multiply MDS matrix by all of this. And the way you can think about this, the evaluation logic is very similar to kind of what you showed and what kind of Rust has, where the whole block evaluates to the last statement in the block. So this is a slightly more complicated function. I didn't show the transition function, but transition function would be almost identical to what I showed before, because this is just taking the one-step state and applying transition function and subtracting that from the next state in the computation. So, sorry. So this is kind of what I had. Let me know if you guys have any questions. There isn't really an upper bound. Oh, so to repeat the question, is there an upper bound on a transition function in terms of the degree? Theoretically, there is no upper bound. You can make it as high a degree as you want. But in practical terms, the higher the degree, the more time you'll have to spend as a prover to generate the proofs. So, and it could grow pretty quickly. So like you could have, let's say, constraints that are degree 3, there would be much more efficient to prove than constraints of degree 16, for example.
Degree P, so if you are in the final with P, and you would have degrees like P half, for example?
That's probably not going to be, so could we have like a very high degrees, like half of the kind of modulus of the prime field or something like that. That's probably not going to be practical for like foreseeable, very far long-term future because that degree is going to be too high. I think something that is practical is probably degree, at this point, probably degree under 20, maybe in like a few years, degree, you know, under 100 or something like that, but not much higher than that. I don't think you can get, you know, I think all the things that I've been working with, they have degree less than an 8, for example, and you try to keep the degree low. You can still do a bunch of things with the degree 8, but you can do some cool things if you could raise to a power of the prime field. You had a question?
Yeah, you mentioned that composability is challenging today, right? Is that fundamental to this approach, or is there like a path?
Well, I think so the question is that it's challenging today, and if that's the constraint of the approach or something else. Did I understand correctly the question? So right now, all kind of zero knowledge proofs are like the prover time is fairly, that's a fairly difficult thing to do. They take quite a bit of time, and you know, it could be measured on the order of like less than a second for simple calculations. But as an example, to prove Merkle tree membership, let's say to a tree of depth 16 using AirScript, you would probably spend about a second and a half on the proof time. But if you had, like, say, 30,000 kind of memberships that you wanted to prove in a single proof, that could extend like beyond a few minutes, potentially even more. And the memory requirements are going to be very, very significant as well. We're talking about like gigabytes and potentially hundreds of gigabytes of RAM. And depends on how you structure your computation. Now, as RAM gets cheaper, as you get more parallelism, and one thing I didn't mention, that SNARKs are extremely easily parallelizable, so you can run them on 32 cores or more, and that will kind of speed up your computations. Within the AirScript, I don't have that yet. Yeah, you could, like, as you mentioned, as hardware progresses and as you get ASICs, for example, to do a lot of the kind of mathematical operations, that could speed up by a factor of 1,000, for example. But kind of hardware is the challenging part. I don't think that's necessarily the issue of the approach. I don't think you can get better than that. And actually, there were like some papers published recently that allow you to do it a little bit faster even, but not by much. All right, thank you very much.
Hello, hello. Hope you guys have been having a good workshop. My name is Brian. Oh.
Hey!
Hello. All right, so my name is Brian.
And I'm Bryce.
And we are presenting today on Dark Forest, which is a project we've been working on with some support from the Ethereum Foundation. Cool, so let's start off with some motivation, and then after that I'm going to give a quick demo. So it's 2019, so of course we're building a decentralized game. But the interesting thing is that for the first time we're able to, with zk-SNARK primitives, we're actually able to build decentralized games which are incomplete information games, and we'll go into what this means shortly. Cool, so let's talk about complete versus incomplete information games. So in game theory, there's this notion of, there's two types of games, complete information games and incomplete information games. Complete information games are games like checkers or chess, where basically the full world state is publicly known by everybody. So if we're playing chess, then I know where your pieces are, you know where my pieces are. Whereas like if we're playing an incomplete information game like poker, then I don't know what your hand is, you don't know what my hand is. There's some public state that's like on the table, but in general, incomplete information games allow for this other dimension of sort of like deception, meta strategies, all this kinds of stuff. So one really like common example of an incomplete information game is like RTS games. So this would be stuff like StarCraft or Age of Empires, stuff where there is a fog of war. So you can't see like your opponent's like position on the map or whatever. And perhaps the most interesting examples of incomplete information games would be like open world persistent MMOs. So this would be stuff like Minecraft Anarchy servers or things like EVE Online. These games have few constraints and they lend themselves naturally to complex emergent behaviors and strategies. And what's sort of interesting about this dichotomy is that up till this point, the Ethereum blockchain most naturally lends itself to complete information games or ecosystems. So this is stuff like CryptoKitties, where everybody knows who owns what cat, what type each cat is, because all that stuff is stored like on the public ledger.
So traditionally, incomplete information games like online poker or like StarCraft are implemented with some centralized server. So there's some server out there that is the source of truth, and it has it's omniscient. It has a total view of the game state, and it shows every player some subset of the game state that player is allowed to see. So how can we do this without a server? How can we make an incomplete information game decentralized? Well, here the only things we have to work with are a network where anything published to the network is public for everyone to see, and players which might maintain some private state. So here the private state is marked S1. So here's how we do this. If the player maintains private state S1, then we require the player to publish a commitment of that private state. This prevents the player from changing his mind about what his private state is to suit his needs later. And we also ask the player to publish a zero knowledge proof that he actually knows some private state S1 corresponding to the commitment he published. And this proof is publicly verifiable. Now let's say the player makes a move, and that move updates his private state to S2. Then in this protocol, we ask the player to publish a second commitment to his new state. But we also ask him to publish a proof, a zero knowledge proof, that he knows states S1 and S2 corresponding to the commitments C1 and C2, and that there's a valid game transition from state S1 to state S2. And if the player were to make another move, then he'd have to provide a valid proof of transition from S2 to S3, and so on and so forth. And you'll notice that as long as all the proofs that the player provides are valid, then the player must have started from a valid state and made only valid moves, so the player cannot have cheated in any way. And note, moreover, that at no point in this protocol do the private states actually get revealed to the network, and we're able to get incomplete information without any centralization.
We'll take questions at the end if that's all right. Yep. Cool. So now what we have for you guys is a demo. I'm going to show it on the screen, and if you want to follow along, you can actually play on the same board as me in tinyurl.com/darkforestgame. Note that you will need MetaMask and ROPS in Ether in order to play, otherwise it'll just say like loading indefinitely. Cool. So on my screen, what I have is Dark Forest v0.0. I'm going to just go ahead and like enter my email address. Your email doesn't like go on chain or anything. This is just for record purposes. All right. So while I'm initializing, I'm just going to talk a little bit about the premise of this game. It's a really simple sort of like space conquest RTS game. And what happens is, there's this large 2D grid. There's a bunch of like planets that like /darkforestgame. Oh, 1 second. I think I'm on the wrong account. This one. Yeah, there's like a bunch of planets on this grid, and basically what happens is you're trying to like conquer nearby planets. Other people like also live on this board, and here we are. Okay, cool. So I've just initialized, and as you can see, there's like this large 2D empty space. Now most of it's obscured by this gray fog of war. You can sort of like pan and zoom and all this stuff, but you'll notice that like I own like this planet over here. That's like denoted by this blue circle. I can do things like pan, zoom, and even move forces between planets. And what that's going to do is on the next block update on the Ropsten network, it's going to like send over some number of ships. Oh. Okay, something's off here. But anyways, what you can imagine happening is basically that like, earlier today I made a move from this planet to this planet. Oh, the transaction went through. Okay, cool. So, and you can see now that like I own these 3 planets instead of these 2. My number of ships is like gradually increasing, and all of this is just being stored on chain. So that's the mechanics. If you'd like, you can also initialize a planet, move stuff around. It'll cost some Ropsten Ether, but hopefully no one's too bummed about that. Let's talk a little bit about what is going on under the hood. So this is an incomplete information game in the sense that like you might also live on this board, but until what's going on here is like a web worker is uncovering the fog of war. Until I like discover your area, I don't know where you are, even though we are on the same board. So specifically, the way that we actually like encode this grid is everybody lives on this large grid, and every position on this grid has some pair of coordinates x, comma, y that identify it. So this coordinate over here might be like 1,000, 1,300 or something. I'm going to define the location's public address, i.e. like a public number corresponding to a location, to be the hash of the x and y coordinates. And I'm going to say the coordinates themselves are the location's private address, and the reasons for this will become clear soon. Furthermore, I'm going to stipulate that whenever the hash of a location is under a certain difficulty threshold, which here is about like 1/2000 of the hash space, that location contains a habitable planet, and all other regions are empty space. Finally, players can own planets. They can have units on them, and these units will like gradually grow over time. All right, so let's talk about what's actually being stored. On-chain, all that we're storing essentially is a mapping from habitable planets to like habitable planet public addresses. So this is like the hash of locations to the owners of the respective planets. And on the client, what the client is doing is it's remembering what are the private coordinates corresponding to the public addresses that like my Ethereum account owns. In addition to this, what it's also doing is every time one of these blocks turns from gray to black, that means that like I've just hashed a 16 by 16 chunk of x, comma, y coordinates, and I've essentially like mined that block in space. So now I know if there are habitable planets in that area, and if there are, I can compare them to what's on the chain to determine whether or not someone else lives at that planet. So you can see like I recently discovered, oh, here's like an enemy who like lives some distance away from me. So someone must have like initialized them in the last couple of minutes. Yeah.
So we also want players to be able to move around and take actions in this game. So here is how that is being implemented. When you want to move from one planet to another, you're giving the contract or the blockchain this set of inputs. So the address you're moving from, the address you're moving to, some upper bound on the distance that you're moving in private address space, and a zero knowledge proof whose purpose will become clear later. And semantically, this moves ships from one planet to another and pays some cost in ships depending on the distance that you move. And the zero knowledge proof certifies that you privately know the coordinates x1, y1, and x2, y2, such that the first pair hashes to the old public address, the second pair hashes to the new public address, and these two coordinates are at most your claimed distance apart. And if all of this checks out, then the contract executes your move. Initialization is handled in the same way. And note that throughout this whole procedure, the private coordinates x1, y1, x2, y2 are never revealed to the contract, and they remain private. So now we'll quickly take you through how we implemented this game. Here is a 10,000-foot view of our stack. You'll notice it's very similar to the snarky diagram that Izzy showed earlier this morning. No surprise, because it's the same technology. So the libraries we use are Circom, SNARK.js, and WebSNARK. Let's see how it works. So we start off with a Circom circuit. Circom is a language that allows us to specify any arithmetic circuit. And the snark that we'll eventually make will let us prove that we know some inputs to the circuit that make the circuit give a certain output. So we write this circuit in Circom and we compile it using Circom into the circuit.json object that SNARK.js can understand. SNARK.js takes this circuit object and produces a proving key and a verifying contract. We'll talk about the proving key first. The verifying contract will come later. So in the game, let's say I want to take an action. I want to make a move, and I need to come up with zero knowledge proof that I know some information. Then WebSNARK takes the proving key that snark.js outputted and the private inputs that I want to prove I have knowledge of, and outputs a proof. And this proof gets sent by the client to the contract. And remember that the snark.js gave our contract a certain verifying key. So when the contract receives the proof from the client, it is able to verify that proof using that verifying key. And if all of it checks out, then the game action gets executed, and your ship's smooth. And throughout all of this, we maintain privacy, and therefore we get an incomplete information game with no centralization.
Cool, so that's basically it. From here, there's just like a couple more things that we'd like to do to make the game awesome. The first is that you can vary difficulty by region and essentially have procedural terrain generation. We can do things like planets are NFTs, and the hashes sort of refer to like color and like different properties of planets. Better graphics. You can have staking on planets. So like if you take over someone's planet, you have literally like taken some of their ETH. And yeah, all sorts of fun stuff. But if you're interested, come talk to us afterwards. Cool.
So I think we have time for like maybe one quick question for that team. And yeah, if anybody has a question, I will call on you if you haven't had a chance to ask one yet, or if there aren't any others, then we can go to you. Does anybody have a question who hasn't had a chance to speak yet?
I have a question.
Okay.
So when you do the verification, this is smart contract.
We do have to make it like a little bit quick too, so if we just, yeah.
Sorry, can you repeat that?
If the smart contract performs the verification, so it's waiting to do that, or how?
Yeah, so the question is, does the smart contract perform verification? The short answer is yes, it does. It costs about 500K gas, but if you do things like optimistically, i.e. you assume good faith, but then trust clients to challenge bad ZK proofs, then you can drive this cost down drastically. So there's a bunch of little like lazy update tricks essentially that we're doing to like make the planet generation continuous and stuff like that.
Okay, awesome. Round of applause for these guys. Thank you all so much.
No, I just wanted to say thank you to everyone who helped make this workshop possible. There were, so many different people from Claire. Everyone can applaud. To Christine, who's back there. To everyone who helped. Oh, sorry.
Okay, just get the screen up.
Oh yeah.
Sorry.
Is it? It's probably gonna go in a second. Yeah. To everyone at O1 Labs who over time have contributed to the software. Nathan, who made the awesome voting example, and so much more, the Docker image, yeah, everyone wearing a T-shirt. Thank you so much for helping throughout the day. I just want to say thank you. Yeah, so without further ado, he doesn't need so much introduction. Probably everyone knows who he is. He's Vitalik. He may or may not be giving away ETH, depending on the day. But anyway, everyone, let's give him a round of applause.
So I guess for my talk, I wanted to kind of turn a bit into the applications direction and look more generally at some of the use cases for different kinds of zero-knowledge proofs and where we kind of in our Ethereum roadmap and our attempts to make Ethereum more private and more scalable and more other nice things have kind of figured out where in the short term it might make sense to apply zero-knowledge proofs, where in the long term, and kind of what are some of the benefits and some of the challenges are. So starting off with Plasma, right? So Plasma, this layer 2 scalability solution that has existed for a couple of years now, kind of as an idea. So first there was Plasma MVP, Plasma Cache, kind of a lot of different variations on it. And one of the things that we've discovered in the last couple of years is that Plasma is actually pretty complicated, right? Like, for the very simplest version of Plasma that kind of is a proof of concept that the thing is useful at all, which is probably Plasma Cash. It's very simple. It's just a bunch of Merkle roots of transactions of assets, but Plasma Cash only applies to transfer of non-fungible tokens. And so if you want to trade digital baseball cards at 10,000 a second with crypto-economic security, you can, but extending that even to regular payments requires defragmentation and other complicated things. And expanding that to atomic swaps and then general purpose smart contract computation becomes kind of more and more difficult for a bunch of different reasons. And if anyone was at my presentation yesterday, and I talked about some of them, right? Basically, Plasma relies on kind of some implicit assumptions about the idea of kind of who's responsible for a particular piece of state, and if how do you, and a bunch of different tricks that involve trying to prove that data that was committed to historically is valid, even if the data might not be available. And it turns out that just basically slapping a zero-knowledge proof on every Merkle root that gets submitted just solves the problem. Or it solves a lot of problems. It doesn't solve the entire problem, it solves a lot of problems. And SNARKware is using SNARKs to basically create a kind of non-custodial version of an exchange, and they've been partnering with Coinbase on this, and they're really doing some good work on pushing this forward. Basically using a Plasma-like architecture plus SNARKs to actually make Plasma for a pretty complex application of trading in an exchange actually work, right? And the reason why SNARKs are really nice here is basically because in a normal Plasma architecture, you have a bunch of transactions. The transactions are off-chain, and you only publish a Merkle root on-chain. And here what you do is you publish a Merkle root along with a proof that says, whatever is in here, we're not going to tell you what it is, but it's valid. And it turns out that if you have this proof, then a lot of the kind of exit game logic that exists in Plasma and of the rules for what happens when you want to withdraw things from the system become a lot more tractable, right? And the reason is, like, first of all, if I provide a Merkle proof, I know that Merkle proof is a proof of state that's valid. And if I publish a full state, that like if you actually publish an entire preimage of a Merkle root, you know that it's valid just because it is the thing that is the preimage of this root. So once you have kind of proofs attached to everything, then a lot of the different and complicated conditions that have to do with, like, oh, let's wait for a challenge period, and let's see if this transaction was a double spend, and if it is a double spend, then here's how you challenge this, and here's how you challenge a challenge. Like, a lot of those things just go away because, like, you know the thing is valid and you know it's not a double spend. Now, it doesn't solve every problem. There's still, like, so for example, in this system, if you want to withdraw, you would still have to wait for about a week. Like, you still need to have a challenge period. And the reasons for this have to do with kind of the possibility that there is an operator that might still be kind of withholding data. So the scenario here is like Alice has 20 coins and Alice withdraws, and then the operator is malicious. The operator publishes some blocks without revealing what the data is behind them is. And it turns out that those 20 coins that Alice tried to withdraw, there was another block to transfer those 20 coins to Bob, and then Bob tries to withdraw them. And if the data is not publicly available, you have no idea that something like that happened. And so you still need challenge periods to resolve some of these situations. But like basically the number of corner cases you have to deal with, even for very complex applications, just goes way down. Right? So that's zero-knowledge proofs for one kind of layer 2 scaling. There's also zero-knowledge proofs for privacy. And so this is zk-SNARKs. I believe it's Graph 16. And this is an application, tornado.cash, and it's basically just a simple mixer running on Ethereum mainnet. Been running for 2 months, and on average about 5 to 6 daily active users, which I guess makes it count as pretty successful. Honestly, having it have like 5 daily active users is good because it means that people can kind of get used to it and start using and running the thing. But there was a security hole a couple of weeks ago, and fortunately they patched it up, and it seems like nobody got hurt. So yeah, the things, like, there's still a lot of flaws in the thing, right? So one big one, for example, is that they only support deposit sizes of 0.1 ETH. And so it's basically like only usable for, like, if you have some amount of coins and you want to send them to some other address, and in that other address, like, you just want to do a couple of non-financial things, and you want to have that address not be connected to the rest of your activity, then it's like kind of useful for that already, right? If all you want to do is just pay for a few transaction fees, it's useful. You know, it's not useful for other things yet, and like realistically, there's still kind of a long way to go. But like, basically, SNARKs are definitely not theoretical, and they're definitely something that you can already build Ethereum applications around and then actually start using them, right? So in this case, basically what they have is they have a smart contract, and the smart contract has 2 parts. One part is you make a deposit. If you make a deposit, it gets added to a Merkle tree using some low arithmetic complexity hash function. And the second part is you can withdraw, and if you withdraw, you provide your nullifier, you provide your zero knowledge proof, and you can, like, if everything matches up, then the thing sends you your money out. Now, there is one kind of subtlety for engineering kind of zero knowledge proof for privacy applications on Ethereum, which is that transactions have to pay transaction fees, and to pay transaction fees, you have to already have ETH. And if basically if you already have, like, if you don't already, or if your job is to try to get ETH into a new account, then from that new account has to already have ETH. Well, where does that ETH come from? Well, if it comes from the old account, then you've made an on-chain link between the two. This system solves it using a kind of layer 2 market. So the idea here is that when you withdraw, your withdrawal is initially, it's not a kind of formal Ethereum transaction. It's an off-chain message. And that off-chain message basically includes like a signature that says, whoever includes this in the chain has the right to collect some fee, and that fee kind of gets sent to this relayer basically after the smart contract verification is finished and after the money actually gets sent to the new account. So this basically with this kind of gadget, this kind of layer 2 transaction sending, it's something that's become more and more of a theme in Ethereum land the last few months. And it has a couple of use cases, right? One of them is privacy preservation. Another one is sometimes application developers want to let their users that they've authenticated in some other way make a few transactions without them having to already have ETH. Sometimes people who have DAI wants to be able to pay transaction fees in DAI. And like these kind of layer 2 gas markets do make all of those things possible. But and fortunately, there is general purpose infrastructure being developed for them, right? So there's something called Gas Station Network, and then there's a thing Tornado's working on. There's Barry's team has something. So like these things are being worked on, and once you have that, then like it's not a piece that people think about, but it's still another important kind of step forward for making privacy applications actually provide privacy. Yes. So you're only, the way that this is done is that you kind of send to the relayer, like just basically the relayer registers their address, which could be IP address, could be DNS, or it could be an onion address. And so like in these systems, there's always the problem of kind of network level privacy. And yes, like you do have to do your own network level privacy essentially. And I think that in general, that's kind of common for all of these privacy systems. I guess I talk about it less because like those are problems to which we already have kind of working solutions, whereas kind of privacy for blockchains is still, like it's kind of much newer that there's any solutions at all. But it's definitely very important to not forget. Yes?
If there's 5 or 6 daily active users for this mixer,
Uh-huh.
shouldn't every transaction in the mixer be tracked to like one of those 5 people?
Yeah, so like you basically, if you want this thing to give you a kind of privacy, you have to like wait days before you take your money out. So it's like basically I think like, it is like privacy is a kind of process, right? And it's like I think the people like realistically kind of everyone who's actually involved in this project, I think the opinion is that this will start becoming useful when it gets integrated into a kind of MetaMask or something, or just becomes a kind of a default part of people's workflows in some form. And that'll happen eventually, like basically when people get kind of comfortable enough with the thing and its security issues. Post-Istanbul, gas costs are going down, and we'll talk about that, and that'll make things more viable. So it's still kind of, it's on the up and up, but it's not a kind of prime time quite yet. Yes? What I perceive about what?
Are there any thoughts about what's the perceived impression of how much mixing happened versus how much might have happened if there was collusion among participants?
What do you mean by collusion among?
Civil attacks, so people appearing for many, many transactions.
Oh, I see. People, so like basically what if like 90% of these daily active users are the NSA? Yeah, I mean, this is definitely a concern, and it's definitely like a reason why you can't just kind of trust daily active user counts without a big safety factor. In terms, I don't get the, I mean, it could be happening. My guess is that it's not, because like right now it's still kind of a very small scale thing, and like there's not too much serious usage yet. But yeah. Any approach to address that? I think it's hard, right? Well, so two things. I guess the long-term solution is basically that like this stuff should get integrated into mainstream wallet workflows, and we kind of trust just from kind of wallets like user counts that there's there's enough people that are participating, and then you add a pretty big safety factor on top. Yeah. So payments step 1, general purpose kind of privacy step 2, and that and I mean Aztec has been working on this, and they basically doing kind of zk-SNARKs, and they're trying to build this as an Ethereum second layer. So and I think there's some other teams doing this as well, but generally, kind of, the more your privacy becomes general purpose, in some ways, the harder it is. I mean, I think the way zk-SNARKs does it is they kind of get around the need to have a VM inside of a SNARK by instead just making it be a SNARK of SNARK verification, and then you get your generality by just allowing different verification keys. But this is still kind of earlier than, or it's still much earlier stage than the things that are like very application specific. So aside from privacy, there is also scalability, and I mean I talked about zero knowledge proof Plasma. The other thing that you have is zk rollup, and so the difference between rollup and Plasma is that in Plasma, the data is off chain. In a rollup, the data is on chain, and the thing that you get from data being on-chain, well, basically two things, right? One of them is that if data is on-chain, then attacks involving data unavailability are not really possible anymore. So if data is all on-chain, then like if you publish a block, then you're publishing kind of all of the data, and so there isn't this possibility that like, oh, if you make this withdrawal and out of data that has not been published, and you get these double spends and nobody realizes what's going on. Basically because in this kind of system, if you can assume all of the blocks are, all of the data in all of the blocks has been published to chain, then you can just force people to only be allowed to withdraw from the most recent block, and when they withdraw, you kind of manipulate the state in real time. So it solves kind of even more problems, and it creates this kind of really clean scalability solution. But the cost is the data has to go on chain. How much data? It turns out not that much. So you can kind of really cleverly compress transactions. And if we want just regular account-to-account payments, you only need about 12 bytes to go on chain. And 12 bytes is right now 748 gas in Ethereum. And with the Istanbul hard fork, it's going to go down to about somewhere less than 200. So basically, the idea behind what ZK Rollup does is it just says, we're going to have a smart contract. That smart contract is going to publish or maintain a kind of Merkle root of like what is the most recent state. And sometimes anyone, sometimes just an operator, sometimes some other scheme, they can publish a block. And a block just says, here's the data, and here's a proof that says that if the state is all valid and there are valid signatures, and if you take this root and then you apply these transactions, then here's the new root. So you take that kind of whole claim, you package it up into a proof, and you verify it. The proof gets verified on chain. And so the guarantee that a user has is they have a guarantee that whatever state is encoded in the root is correct. And they also have a guarantee that because enough data to process all the state transitions has been published, they have the ability to kind of personally regenerate the entire state if they want to. And so either use that information to withdraw any coins or use that information to become an active participant. So I think like, Matter Labs made a version of this and tested it on chain and got somewhere over 100 TPS a while back. The main challenge with this scheme actually is right now not so much the blockchain, it's just limitations in the kind of efficiency of proving software and hardware. So we can talk about kind of security-focused applications, post-quantum aggregate signatures. So this is, lots of people talk about post-quantum signatures, and there's lots and lots of algorithms for this. ETH2 in particular cares very strongly about aggregate signatures because we have lots of validators, and we expect there will be lots and lots of signatures flying around, potentially tens of thousands per second. And so right now we rely on a BLS aggregation for this, and BLS aggregation for this is really nice because with BLS signatures, every signature is just an elliptic curve point. You take your elliptic curve points, you just add them all up, and you get an aggregate signature, and it's really that simple. And so aggregate signatures are kind of easy to aggregate, they're tiny, and the amount of data that you need is basically kind of 1 bit per participant to say whether or not they participated in some aggregate. So this is all really nice, but we want a post-quantum alternative, right? So like, we have post-quantum, hashing is post-quantum, regular signatures, we have post-quantum alternatives, we want post-quantum aggregate signatures. And SNARKs seem to be kind of a reasonable contender for the thing that can be used to implement this, basically because with a SNARK you can just make a big, huge, one single proof that just says, oh, here's a whole bunch of signatures, and for every one of these public keys, there exists, say, a Lamport signature that verifies what's against some particular message and some particular public key. So the reason why we want SNARKs here is because SNARKs are kind of the only one of the zero-knowledge proof family right so far that is quantum secure, and Lamport signatures the simplest quantum secure signature, and so you just kind of do one on top of the other. Now, there are kind of viability concerns with this design. So a Lamport signature requires at least kind of 128 hashes to verify. And if we're going to SNARK 128 hashes multiplied by 10,000 participants, SNARKing 1 million hashes, which is for now a lot, right? But I guess, so this, there may be other techniques for this, right? But this is the sort of thing where, like, fortunately, quantum computers are still far away, and so there's still kind of a lot of time to try to figure out ASICs, figure things out in general. But it's a kind of direction that's still worth looking toward. verifying consensus computation. So far I've been, well, mostly talking about kind of layer 2 use cases, but there is also layer 1 use cases. And I mean, code has obviously been kind of the chain that's gone kind of the most all the way, because it's kind of trying hard to put its entire state transition function inside of a zero knowledge proof. But in the case of kind of a fairly complicated general purpose computing platform, that's a kind of more distant dream. And so the shorter term dreams are basically, can we provide zero knowledge proofs for kind of very specific components that are general purpose, but that are also kind of computationally intensive, and see if we can kind of get a lot of gains out of that, and then you kind of move further and further on from there over time. So data availability erasure coding, this is kind of this is a topic that I've been kind of talking about for the last couple of years. And the idea here basically is to have a way to prove to light clients that have not downloaded a full block that the full block actually is available, right? So this could be usable for something like Plasma. This could be usable for layer 1 blockchains. Basically, any situation where you rely on fraud proofs for security, but fraud proofs don't work if someone publishes a block with a bad root where they just don't publish the rest of the data. And so the challenge here is, well, can we kind of come up with a mechanism that lets people verify probabilistically that some piece of data has been published without them having to download the whole thing? And the technique that I proposed is basically this kind of random sampling technique that says, oh, instead of downloading this big, huge piece of data, you would randomly select some number of indices, and you would just ask the network for Merkle proofs of the data at these particular positions. And if you make 40 checks and then you get all 40 replies, then that implies with high probability that all of the data is available, or rather that implies with very high probability that more than half of the data is available. And if the data is erasure coded, then if more than half the data is available, you can use that to reconstruct the whole thing. So I have a paper about this kind of with Mustafa Al-Bassam from 2017. There is also a more recent work on something called coded Merkle trees that kind of makes a kind of fraud-proof based kind of improvement on this kind of design. But one challenge in this kind of architecture is, how do you actually prove that the Merkle root is correct, right? Because you can construct an erasure code incorrectly, or you can do some hashing incorrectly, or you could just have random junk in the middle of the tree. And it's basically like, how do we prove to users and let users verify for this really big hunk of data that the Merkle root is correct without those users needing to kind of actually download the whole thing and check it. And one of the proposals here is to just basically use a SNARK for this. And it turns out that kind of if you do the numbers, this kind of actually is within the realm of possibility, which is really interesting. And because this is a kind of very structured kind of computation, like basically what we're doing is you're just building up a Merkle tree root. So all you do is you just kind of lay the hashes down on a line, and then you keep on saying this thing is the hash of its two parents. And so the computation is kind of very mathematically nice and easy to work with. It's not quite a kind of linear computation, because you do need, like, individual nodes in the tree do have to look back to kind of two parents, but it's still kind of close to it. And so this is one of the applications that kind of is more practical than some of the other ones. Example 2, compressing Merkle witnesses. So we have recently been going in this, what we call this kind of stateless client direction. So a stateless client basically is this idea that if you have a block and you want people to be able to verify that block, but without having to already have the entire state, and because the state is big, because the state takes like 5 hours to download because you don't want people to be hitting the hard drive so often because hard drives are still slow. Then what you can do is you can have this approach where along with a block, you provide Merkle proofs of all of the pieces of data that it accesses. And so if you don't have the state, you just have a root hash of the state, then you can basically use these Merkle proofs and you can just verify for yourself. Like if we have a transaction that says, I'm Alice, I have 100 coins, I'm sending 40 of them to Bob. Bob had 10 coins, I'm going from 100 down to 60, Bob is going from 10 up to 50. You would give Merkle branches of Alice's balance before, of Bob's balance before, and anyone that has those Merkle branches could kind of process the block, execute the transactions, and verify that the root hash of the state after applying the changes is what the block claims it to be. So this is a kind of really nice approach because it basically, it solves a lot of problems, right? Particularly, it basically lets us go down from having 3 resources that we have to balance between, which are computation, state storage, and bandwidth. It lets us go down to 2. So you just have computation and bandwidth. And that's kind of a significantly more tractable problem just in terms of kind of block gas limit engineering, kind of consensus economics design and all of these things. But it has a problem, right? And the problem is that Merkle witnesses are pretty long. Now, they're not too long, so if you don't do any of this, you are fine. So basically, every one of these Merkle branches is going to be, to access an account, maybe about 800 bytes, right? And in Ethereum, for example, post-Istanbul, 800 bytes multiplied by 16 gas, it'll still be 12,800 and gas. But so it's maybe kind of about 1 order of magnitude more expensive than accessing accounts is right now. But it's still, and like potentially we're still kind of underpricing storage and overpricing data, so kind of pushing it up is a good thing. But it still would be nice to be able to kind of fit more transactions and fit more account accesses into a block. So the proposal here is basically you use a SNARK or whatever else to basically just say, instead of having all of these Merkle branches, we're just going to have this kind of table that says, here are all the accounts that were accessed, here were their balances before, here are their balances after, and we're just going to have a proof that says, if you accept this table, then if you accept this previous state hash, then here is the new state hash. And now, verifying that the table is correct is still something that you have to do locally. You still have to like run EVM computation and all of those things. But if you have the table, then the process of verifying that given this state, like this state transition of like what Bob's balances are going from what to what, Chowry's balance is going from what to what balances you're reading, and like verifying, once you have that table, then verifying that that corresponds to the Merkle root changing from this value to this value is something that can be done inside of a SNARK or a SNARK, and once again, it's this kind of very highly structured computation, and so it's also an opportunity for some kind of pretty short-term efficiency improvements. Now, the long term, of course, is the whole state transition function, but this involves zero-knowledge proving general-purpose VM execution, and this is hard. So longer term, but fortunately, there's shorter-term things. So, yes?
What's the implication of that last step? Like, what would we get by doing zero-knowledge proofs for the whole EVM?
Basically, like, clients so actually, so you know how stateless clients go from reducing from 3 resources you care about to computation, storage, and bandwidth to 2 resources, computation and bandwidth. If you ZKP the whole state transition function, then you're basically literally going down to just 1 resource, which is the bandwidth, right? Because clients would still have to download blocks, and because like data, like SNARKs, there's a bit of a misconception, right, that like zero-knowledge proofs can kind of fully verify everything. The reality is that there's one thing they don't verify, which is data availability. And if you publish a block which is valid but where you hide the data, that's still a really, really bad and nasty thing, because you could use that, like for example, to censor people by denying them the information they need to make their own Merkle witnesses. So you still would need to download blocks. You still would need to download at least the present state to verify its availability. But bandwidth is increasing faster than computation. Bandwidth is more homogeneous, so it's less vulnerable to security issues than computation. And in general, kind of having one resource to rule them all solves a lot of economic questions because you don't have to kind of centrally plan the ratios between the two things. And also in general, like for example, right now, for the Ethereum blockchain, it's known already that the biggest bottleneck is state, then the second biggest bottleneck is computation, and then data is the one that's actually fine. Yeah. So implementation, right? So when the Ethereum platform was originally created, we didn't even think about zero-knowledge proofs. And because at the time, like I had just heard about SNARKs from L.A. Ben-Sasson from the first time, and this was a kind of a simpler era when SNARKs were still considered moon math and like very kind of spooky far away stuff. And so the kind of the computational engine that we had was still kind of very simple. But then over time, as zero-knowledge proofs became more and more practical, Zcash started kind of launching, and like, wow, you can use this stuff to make internet coins now. So we had the Byzantium fork. So in this kind of the Byzantium fork, this was this kind of Ethereum network upgrade that we had about 2 years ago. We added support for doing elliptic curve additions, elliptic curve multiplications, and elliptic curve pairings over the AltBN 128 curve into the virtual machine. And people started building things on top of this. And people started building kind of simple things at first. There were kind of experiments that were done as part of like academic boot camps. But now there's more and more things that are being built, and now there's things like ZK rollups and kind of and mixers and kind of anonymous voting things and other fun stuff being built on top of this. Now, good news. So after Byzantium came Constantinople. After Constantinople is coming Istanbul. This is the name of Ethereum's next hard fork. And there's kind of two big changes that are kind of, like, a lot of the changes have to do with gas costs, and there's two big changes that are coming, right? So the first one is that a SNARK currently costs somewhere between 200 and 500,000 gas, and this is because like basically pairings and elliptic curve multiplications are expensive. The major client developers have basically all discovered kind of more efficient libraries for doing SNARKs, and so for doing elliptic curve operations. And so we are decreasing the cost of all of these by a factor of about 3. Right? So pairings are going down from 80,000 per points plus 100,000 per pairing check to 34,000 per point plus 45,000 per pairing check. Multiplications going down from 40,000 to 6,000, and additions going down from 500 to 150. So SNARKs are probably going to decrease from this to like potentially maybe only a bit over 100,000. So a lot more viable. And also STARKs, right? So STARKs are kind of our other major zero-knowledge proof family friend. And right now, STARKs are expensive, mainly because data is expensive, right? So the current gas cost of a STARK is about 6.3 million gas is a number I pulled off of the a recent transaction on StarkDex, but I mean STARKs are kind of O of n log squared n, and so their size is always going to be variable. But so it's not like exactly 6.3 million. It's like sometimes 4 million, sometimes 6, sometimes 8. And about 2/3 of this is cost of data. The remaining 1/3 is finite field operations. And in the Istanbul hard fork, we're reducing the cost of data from 68 gas per byte to 16 gas per byte. And so the data portion goes way down. And so the new cost of a STARK becomes about 3 million, which also means that if you're building an application that involves submitting a SNARK along with submitting a whole bunch of other stuff, instead of there being 3.7 million gas of space to do other things with, there's 7 million gas of space. So cost reductions for both SNARKs and STARKs. And I guess longer term things have application and implementation wise. And obviously there's all of these kind of fancy new zero knowledge proof protocols coming out. One of the good things about Ethereum taking a kind of relatively layer 2 approach to them is that like whatever new scheme you want to use, whether it's like Plonk or Marlin or Fractal or Sonic, whatever buzzword of the day, like you can, it's all just opcodes, right? And you'd have to write a verifier in Solidity or Viper or whatever you use, but it's all opcodes, and you can just go ahead and do it, and it'll be pretty viable right from the start. The one thing that's kind of challenging is that you are basically limited to using the alt-BN128 curve. And like there's people talking about kind of considering changing that. The main problem here is basically that like making a general purpose elliptic curve general purpose elliptic curve support is kind of pretty complicated. So in Ethereum we have this kind of precompile system where like you have the virtual machine, but the virtual machine is slow, and so we have kind of hard-coded special purpose operations that get accelerated. Elliptic curve computations are one of them. And if you wants to kind of for every one of these operations that gets accelerated, you have to fully specify like what the logic behind all of them is and what the answers are under pretty much all conditions, right? And this has to be formally specified, tested, different implementations checked against each other. You can't have any mistakes. And for one elliptic curve, you can do this. But if you try to do this for like every elliptic curve, you start running into issues like, oh, some of them have cofactors, some of them don't. Oh, how do you even prove whether or not this thing is a curve? Because what if the modulus is not even prime, and it's like one of those weird, funny Carmichael numbers where you can't even tell it's not prime. So then, like, if it is one of these edge cases, then like which specific algorithm do you use? And like there are people that are trying to push for like some standard way to do general purpose elliptic curve things, but it's like it's complicated because like that really would increase all the edge cases. So it's like it's not necessarily clear we are going to get like general purpose elliptic curve things. And I mean we could end up getting like support for a few extra curves, and I know there's like specific ones that people want to use for things like compatibility with Ethereum 2 or the ability to support kind of like some depth of recursion and things like this. But like this is the one area where unfortunately kind of Ethereum's dream of being general purpose and you can do whatever you want in the sandbox doesn't quite apply. But we try to come close and kind of balance things. So for kind of layer 2 use cases, there's stuff being built. And then for layer 1 use cases, and it doesn't, like for layer 1 use cases of zero knowledge proofs, things like, we can't just say like you build your own layer 1 because like there's one layer 1 in any given blockchain. So we would have to kind of pick one protocol and enshrine it to some extent. And this is something like, and there's kind of complicated challenges. I've made some kind of ETH research posts about some of the issues, but it's still early stage. So, thank you. Yeah. Yes.
So, which regime is like checking Carmichael numbers or formality parts? Like that comment really confuses me.
Yeah, I mean, I know that the kind of the primality tests for it exist, but the problem basically is that like we're talking about an elliptic curve kind of precompile where someone's just saying, here's some curve parameters and here's a point. Give me a pairing on this thing. And like basically if you have to kind of do one of these kind of universal primality tests, then it just ends up being too expensive. Yeah. Good question though. It's needed to correct that. And also aside from that, there's also just kind of fear of raw just consensus complexity, and it's like those algorithms are not simple. Yes.
Having just one cube,
Hmm?
which kind of limitation pose, despite the fact that I cannot experiment with other cubes?
If there's just one curve, then what? What's the question?
We said that having possibility inside the virtual machine of having many different elliptic curves.
Mm-hmm.
We have only one,
Mm-hmm.
which is basically the limitation we have.
Mm-hmm.
I would say technically on things that we can do.
Oh, what's the limitation? So anything that's kind of simple pairing-based cryptography, SNARKs, any like Planck, Marlin, any of these new families, like you can do all of that stuff. The things that you can't do efficiently have to do with basically doing zero-knowledge proofs over computation that itself involves cryptography, or like that itself involves pairing-based cryptography. So like like recursive SNARKs, you can't really efficiently do. I think for the AltBN 128 curve, like there is this kind of baby jub curve that someone generated. So you can do like simple cryptography kind of being proven inside of a SNARK efficiently, but like SNARKs of SNARKs or SNARKs of pairings is not really practical. I think that's probably the main thing. In like ZEXE, for example, does kind of end up theoretically depending on like at least one level of recursive snarking. But I know there are also kind of ways to just like take that inefficiency and just kind of doing computations with mismatched moduluses and just dealing with it. So this is still a kind of an evolving space. Yes. Okay, one more.
I was wondering, maybe this is even way far off, but could there be something like snarkify becomes like a first-class citizen keyword in like Solidity or something like that? And that could just wrap some expression.
Yeah, and it definitely is far off. I mean, okay, I guess in Solidity would be easier than in the EVM because the main challenge is that these algorithms are not standardized yet, right? And like, there's fancy new things that came out literally 6 weeks ago. So agreeing on one single algorithm at EVM level is something that's still just, but agreeing, and also just because there's all these arguments about like different flavors of zero-knowledge proof with their different kinds of assumptions, and like, are trusted setups evil, are hidden order groups evil, like are proofs being really big a problem? Do you care about prover time? Do you care about verifier time? At the higher level language layer, I think those things are less serious because like, if Solidity decides to use like, snarkify based on graph 16, and a bunch of people are like, no, we want the full generality, we want Planck, and then like Viper can just go and add its own snarkify keyword that uses Planck. So it's high-level languages are kind of one step removed that kind of allows more of that experimentation and competition. So I guess that could come sooner, but it's definitely still some time away.